All right, welcome back. So this is going to be part 2 of lesson 3 of the Fast AI course. Last video in part 1, I made it through an hour of the course of the video, but I spent a lot of time on the course. I spent like 7 hours on the course because there was an exercise they wanted us to do that would that took a long time and a lot of people had trouble with. So let's go back to the Discord server and we'll go over to the chat. So you can see here's the final result. I uploaded a picture of myself just to test it. I'm a black bear, but I'll show what I figured out. So I didn't have the pickle file. Definitely going to need that. That's the most important thing. And the reason that's important is because it allows you to start your code with this learn_inf equals load learner for that pickle file. If you don't have that, you're going to need to train your model. We're not going to be able to train our model on the server that people will use to use our model, because that server doesn't have the GPU as the server will use to train the model. So we're going to have to use two different servers. We're going to use one server to train the model and export the file, the pickle file. And then we use another server to load the pickle file and then classify our images, actually use the result, use the model. So we need one server to create the model, and that server has to have that high-powered, expensive GPU. And then we can basically use any server we want to run the model. It does need some bandwidth, especially depending on your pickle file. Those files can grow pretty fast too, so they can end up being pretty big files. But that second server to use the model requires a lot fewer expensive components as that first server. And that's a reason why in lesson 1 he thought it was a myth that you needed access to expensive equipment, because when you use pre-trained models, the way you use them is just by loading these pickle files. So all you need is a pickle file to use a pre-trained model. You don't need access to a expensive GPU to do machine learning. But the problem is you can't train your own models, and you have to trust that your model was trained by somebody else in good faith to your intentions. So, and that's often impossible to ask for, because the person who made it just doesn't know what you want. So, in my opinion, it's probably most of the time better to train your own model, but you know, you can save yourself $2,000 and anywhere up to $10,000 by using, or more by using a pre-existing model. So that's where all the potential is going to come from. But if you do that, you're not going to be, I think, using your model for professional experiences. Once you start getting to professional, high-level machine learning, in my opinion, you'll probably need to be training your own models. Using pre-trained models just, I think, is too risky. But an amateur like me and stuff, like learning how to use pre-trained models, I mean, I could have ended up learning, hey, you know, pre-trained models work better. I don't need access to the GPU because somebody already did it for me. So I'm mainly just speaking to the status quo, but things may change very rapidly if it turns out that pre-trained models have more flexibility than was initially thought. Okay, so now I will show the, so first thing I'm going to do is launch my Paperspace. And then I will pull up the code and demonstrate the code that is no longer necessary, because it is only required for training the model, but not for using the model. Okay, but the bad news is this takes at least 5 minutes to boot up, so we're gonna have to find a way to spend that time. So, um, yep. So of course, I think the most obvious thing to do in that time is just to pull up the video and make sure and get to the 1 hour mark on it. So this is lesson 3. Another thing we can do is work on the questions. But yep, so it looks like it saved my spot. Perfect. Let's work on the questions while that is coming up. There should have been some answered already by now. So in addition to the Discord, we're also going to need the book. Okay, so oops, and yeah, I won't need the Discord anymore. I'm gonna need my Google Drive. Google Drive, not Dive. Okay, perfect. So now I can go to my Google Drive. I'm probably gonna need to switch it over. Yes, I am. That's totally fine. Okay, excellent. I switched it over. So now, aha, so here's the questions. They're part of lesson 3. You know what I might do? I might just, well, I'll just keep them there, and then I'll move them later once we're done with lesson 3. And I would like to do this, create an image recognition model using data you curate and deploy it on the web. I know how to do that now. I think it would happen really good. So one thing I would like to do is make things even easier on myself. And oops, well, this isn't up yet, so never mind. Let's do the questions. So which letters are often used to signify the independent and dependent variables? Okay, so here's information about the independent variable. The independent variable is the thing we are using to make predictions from, and the dependent variable is our target. In this case, our independent variables are images, and our variables are the categories, types of bears for each image. We will see many other types of block in the rest of this book. Oh, so these are blocks. Okay. So I don't see anything about, oh, I see. The independent variable is often referred to as x, and the dependent variable is often referred to as y. So let's copy this over, and we'll do two answers here, A and B, and we'll say, okay, and then we'll say, yep. All right, so what's the difference between the crop, pad, and squish size approaches? When might you choose one over the others? So this part I remember as well. So let's do this in 4 parts. We're gonna have the difference. And then we're going to have, after the difference, we're going to have the answer to the second question. When might you choose one over the others? Okay, so let's find out that answer. Don't need my drive open anymore. Crop, pad, and squish. Okay, so by default, resize crops the images to fit a square shape of size requested using the full width or height. This can result in using some important details. Alternatively, you can ask, okay. Okay. So crops the images to fit a square shape of the size requested using the full width or height. This can be, the crop might lose the edges of the photo. Okay, so the next part is going to be pad. So okay. I need some more water. I'll be back shortly. Alright, so I'm back. This whole part looks like it's going to have the answer, so let's read it. All of these approaches seem somewhat useful or somewhat wasteful or problematic. If we squish or stretch the images, they end up as unrealistic shapes, leading to a model that learns that things look different to how they actually are, which we would expect to result in lower accuracy. If we crop the images, then we remove some of the features that allow us to distinguish between similar breeds. That allow us to perform recognition. For instance, if we were trying to recognize breeds of a dog or cat, we might end up cropping out a key part of the body or face necessary to distinguish between similar breeds. If we pad the images, then we have a whole lot of empty space, which is just wasted computation for our model and results in a lower effective resolution for the part of the image we actually use. Instead, what we normally do in practice is to randomly select part of the image and crop to just that part. On each epoch, which is one complete pass through all of our images in the dataset, we randomly select a different part of each image. This means that our model can learn to focus on and recognize different features in our images. It also reflects how images work in the real world. Different photos of the same thing may be framed in slightly different ways. In fact, an entirely untrained neural network knows nothing whatsoever about how images behave. It doesn't even recognize that when an image is rotated by 1 degree, it is still a picture of the same thing. So actually training the neural network with examples of images where the objects are in slightly different places and slightly different sizes helps it to understand the basic concept of what an object is and how it can be represented in an image. Here's another example where we replace resize with random resized crop, which is the transformation that provides the behavior we just described. The most important parameter to pass in is min scale, which determines how much of the image to select at minimum each time. Okay, so what is the difference between size approaches? When might you choose one or the other? So, okay, that's crops. Let's look at pad. Okay, so pad adds zeros seen as black bars to the image in order to maintain the aspect ratio of the original image. Okay, so squish
So what does squish do? So here's squish. So squish scrunches, squish changes the images so that they fit into the box. It does not, it does this by distorting the image. Okay, so when might you choose one over the others? So in general, it is best to use a combination so that your model is trained using more complete data. However, if you do not have a lot of computational power, you can save a lot of computation by only using one of the methods. Especially pad if you make a tweak so that the padding is not processed. Okay, what is data augmentation? Why is it needed? So this is kind of a similar answer to what I said up there, but let's get the book's official answer. So data augmentation refers to creating random variations in our input data such that they appear different but do not actually change the meaning of the data. So there we go. And let's answer why it is needed. Okay, I guess it doesn't really say why it's needed. But I mean, I know why it's needed. Yeah, so here's the answer to that. Training the neural network with examples of images where the objects are in slightly different places and slightly different sizes helps it to understand the basic concept of what an object is and how it can be represented in an image. Okay, so what's the difference between item underscore TFMS and batch underscore TFMS? Okay, so item transforms, TFMS stands for transforms, are pieces of code that run on each individual item, whether it be an image category or so forth. So here you're resizing an individual item of your database. Okay, so let's answer batch transforms. Let's see what those are. Okay, it transforms transforms a badge. Okay, so let's see what a confusion matrix is. So it allows you to view the results of your model. Yep. And see if there are mistakes and what those mistakes are. Okay, so what does export save? I think I know this one off the top of my head. A Python PKL file. But let's take a look at the book. Yep. So a file called export.pkl. What is it called when we use a model for getting predictions instead of training? Okay, so when we use, we call it interference. Oh, inference. Oh, okay. Ah, okay. So this is why it's INF, because it's inference. So we're using inference. That's what it means when you export. So this is a yeah, this or my here, this is code that uses inference instead of AI. An AI model uses inference, and that's why it's INF. Okay, so what are IPython widgets? IPython widgets are GUI components that bring together JavaScript and Python functionally in a web browser and can be created and used within a Juniper notebook. All right, when might you want to use CPU for deployment? When might GPU be better? So use CPU for inference, use GPU for, oh, not BGP, GPU for model training. Yeah, so as you now know, you need a GPU to train nearly any useful deep learning model. So do you need a GPU to use the model? No, you almost certainly do not need a GPU to serve your model in production. There's a few reasons for this. So yep, I got that right. I knew that off the top of my head. I discussed that earlier. Okay, so the next one is going to be, what are the downsides of deploying your app to a server instead of to a client or edge device such as a phone or PC? Here we go. So we also suggest that you iterate from end to end in your project. That is, don't spend months fine-tuning your project, your model, or polishing the perfect GUI or labeling the perfect data set. Instead, complete every step as well as you can in a reasonable amount of time, all the way to the end. For instance, if your final goal is an application that runs on a mobile phone, then that should be what you have after each iteration. Oh, okay. Well, let's see here. Downsides. Let's see if that shows up. Oh, I see. Okay. So there are downsides too, of course. Your application will require a network connection. Okay. So on a server, your application requires an internet connection. On a client or device, oops, and it's going to be your, not you. And then there's going to be restaurant, and there will be latency. Yep. Oh, okay. Well, there could be latency, but you can run it on. Yeah. So here we go. On a, you are limited to the hardware ability on that device. So processing might be much slower, so much slower that the added latency from an internet connection much slower that even with the added latency from the internet connection, communication with a more powerful machine over the internet could end up being faster. Yeah, okay. Scaling the application up is a lot easier because the hardware responsibility is handed off to the user. So horizontal scaling. The data may also be more secure because it is on a private device and not sent over the internet, and then vice versa for all this. Okay, so I think that adds a satisfying answer there. So what are 3 examples of problems that could occur when rolling out a bear warning system in practice? So A, oops, B, and C. Okay, so let's see what the 3 problems would be. Yep, nighttime images. So let's just say images not in the data set. Slow results and slow results and poor camera quality. Poor camera quality or camera shot. Okay, so what is out of domain data? So just one more general problem of out of domain data. That is to say, there may be data that our model sees in production, which is very different to what it saw during training. Okay, so what is domain shift? Domain shift is where the type of data that our model sees changes over time. So let's say, so a good example of this is, let's say you're detecting bears in the park with a bear detection system, and it gives a warning every time there's a bear detected. But let's say the bears get annoyed by that warning, they move out of the park, and now cheetahs are in the park, and cheetahs just start killing all the campers. Your bear detection system isn't going to detect the cheetahs, even though the cheetahs are causing the same problem that the bears were, and you need the video detection system for the same reasons you needed it for the bears. But it's not going to automatically know that what you have it for, the reason you have it for, is to prevent campers from dying, instead of instead of actually detecting your bears. That's not what you're actually trying to do. You're not trying to detect bears. You're trying to prevent campers from getting mauled by bears, even though it's probably far more likely that the bears will be harmed by the campers. But yeah, so yep, so that's domain shift. Although in Alaska, I've been to Alaska, it is the state law when you go out into the bush that you have to have a gun. So bears in Alaska are actually pretty dangerous. There is a pretty good chance of being mauled by a bear if you don't have a gun. All right, what are the 3 steps in the deployment process? Manual process, limited scope development, and gradual expansion. Deployment. And then development expansion. Oh, gradual expansion. Okay, so how is a grayscale image represented on a computer? What about a color image? We're going to have two answers for this. So let's take a look at it for a grayscale image. Okay, so this is probably chapter 3. Yeah, I would think that this is chapter 3. So let's look at chapter 3. Oops, actually, it might be chapter 4. I'm not sure, but I think this I haven't gotten to yet. So let's see if nope, it doesn't show up there. Here we go. So yep, now we have information about the rest of these questions, but I haven't watched the video yet that goes over this. So that's what I'm gonna do next. Before I do that though, so I won't need, oh yeah, I am gonna need this open. So this is from my Google Drive. So one of the things I wanted to demonstrate, and I apologize, I could have demonstrated this earlier. I just kind of forgot that I could have. Is how to generate this. So you've got to have a slash at the end. That is absolutely necessary. And then even though this file is not going to be under this directory, if we go, we can see it's not under that path. It's not in the render directory. It's not in the voila directory. We still need to include this there. And then the key, the most important thing, is this requirements.txt. So you can see I do have voila there, but for some reason I didn't need any of the voila code at all. So I wonder if maybe utils has something that uses it. Nope, I don't see anything. Nope. Okay, so yeah, I'm not sure why that voila was there, but if I click, and you've got to change it over to URL. So now if I click launch, it takes a long time. We do have a build logs here that a lot of the reason I was able to figure out why everything was breaking was looking at those build logs. So if you ever get the chance to see logs, it's always important to take a look at them. Now it says here we're executing 1 of 8. That's going to be for each of these 8 cells here. So when we're finished executing that, we got what was showing up in the last cell. So now I can upload my photos. I've got a test image here which has a grizzly bear in it, and we can see it correctly identified it as a grizzly bear with really good confidence. So it's working. I can share this link with people. They can go and use my tool here. Not sure how long the link persists, but it is a great way to quickly demonstrate things. Okay, so yeah, that's all I wanted to say about that. I guess the other thing I wanted to do, now that my Paperspace console is open, is launch the files here, and then go back into NBS. And then what I would like to do is give it a name that is more that is better. So
we'll do inference, and then we'll do train. So we'll have code that can inference, and then we'll have code that can train. Because if we go back here, we can see what is it called when using a model for getting predictions instead of training. It's called inference. So we're going to rename this here to inference. Okay, and then we'll have another one called training, and then we can very easily come and do any images thing and have this work out, I think. Yeah. So now I'm going to create a new notebook file for Python 3, and it's going to be named training. So we've got two of them now, and it's called inference and training. So let's go back. Oops, before we go back, let's hit the save button. There we go. Now let's go back. And let's do new folder. And we're gonna do, we're gonna rename this folder My AI Projects. Or let's just call it My Projects. I think I don't like it looks bad. Okay, so we're gonna say My Projects. Okay, and then we're gonna move training and inference over to My Projects. I wish I knew how to do that. I guess one thing I can do maybe is copy these two projects. Yeah, so I can duplicate. No, I'd like to. Maybe what I can do is then move into here and now select duplicate. You know what I can do? I can create two empty notebooks here and then fill them in. So this one's going to be named training. Okay, and then we'll save it. We'll go back. And then we're going to make a new notebook again. And it's going to be inference. Okay, so we'll save this and we'll go back. Okay, and now the inference notebook is going to be it's going to match this one. So nope, that's the training. So it's going to match the inference one here. Okay, so we can hopefully copy all of these. Yep, so we're going to copy this cell, and then we're going to, before we do that, we're going to open another instance of Paperspace. We don't need Binder anymore. We don't need. I guess we do need. Nope, nope, nope. So what we can do is instead of copying it from there, we can copy it from there. So let's make another folder, and we'll say folder, and we'll call it their identifier. Okay, and then we can delete these. Okay, and now we can go here and we can create 2 more. Okay, this one is going to be the inference. Okay, and now we can just copy the cells and paste them in one by one. There's only 8 cells, so we got the luxury of doing that. If there were more cells, that would be more difficult. I mean, we could do all the code in one cell, but I think I'd rather have multiple cells. Another thing we can do is save some of this. I don't think we're going to need to clear the output here, so I could remove that. I'm not going to do that just because it's working really well. I'm kind of the school of thought when it comes to code that the goal of reducing your number of lines of code is really just not relevant. It's just not an important goal. Now, increasing the efficiency of your code, decreasing the runtime of your code, that sort of thing, yes, absolutely. But the number of lines in your code, I just don't think that's important at all. Okay, so this is the notebook named Inference. So let's save it, and now let's build a stripped down notebook named Training. So it's going to be, okay, so we'll create a new Python 3 notebook, and we'll call it Training. Okay, so this is going to have all of the code associated with training. So let's go to chapter 2. Okay, so here's where it starts. Oh, nope, never mind. So this learn.export. Oh, okay, yeah. So this is going to be the last line. So let's start with the last line. Okay, we'll insert a cell above. Okay, and now we'll add the rest of the code. So here's the cleaner. This is a widget, so there's interactive things. Now here's the kind of biggest thing. This is where we actually tune the model. Okay, so here's where I'd be better off using an API like Pixabay. I'd get more images and I'd have more flexibility, but I just wanted to get this to work was the most important thing, and I accomplished that. But as far as the code for this stripped down book is concerned, I will want to change it eventually to be more useful and flexible. Okay, but now I've got the stripped down, easy peasy code, and technically I'm only going to need the training code in my Paperspace because this is the server that has access to the high-powered GPU, and the inference notebook I'm only going to need on GitHub so that I can use Binder and make it available for use. And of course I can just use it in here as well. Oh my god. And I'm getting a lot of messages in Discord, it looks like, so I'm going to read some of those. Oh, here we go. Okay, yeah. Somebody else has been working on this, it looks like. So, online talk, we got our highlight so far about the classroom, fire alarm story. How do they say argument being yeah, that's true. Oh, is that happening right now? It is happening right now. Camera failed because I'm using it already. Okay, you know what? I'm gonna pause and then we'll come back. All right, so I took a super long break, multi-hour break. I think I stopped this morning, but let's keep going through. Unfortunately, I might not get through everything, and I wanted to, yeah, it looks like my thing expired as well. I wanted to do some kind of cleanup on some stuff, but I think what we're going to focus on now is we're going to spend an hour or so, stop around 7:30, and just try to get through the whole video, maybe even get all these questions answered, and hopefully that will be enough to be prepared for Monday. But I will restart my notebook just in case I need it. Okay, but now let's focus on getting the rest of this video watched.
So one of the things that really helps, I think, when building a new model is to kind of start with something simple and gradually scale it up. So we've created an even simpler version of MNIST, which we call MNIST sample, which only has 3s and 7s. Okay, so this is a good starting point to make sure that we can kind of do something easy.
Okay, and I can't quite follow along yet because my Paperspace isn't up, but as soon as that is up, I will pull up this book and follow along.
I picked 3s and 7s in this sample because they're very different. But I feel like if we can't do this, I'm going to have trouble recognizing every digit. So step 1 is to call untar data. Untar data is the FastAI function which takes the URL, checks whether you've already downloaded it. If you haven't, it downloads it. Checks whether you've already uncompressed it. If you haven't, it uncompresses it. And then finally returns the path of where that ended up. So you can see here, urls.mnist sample. So you can just hit tab to get autocomplete. It's just some location, right? It doesn't matter where it is. And so then when we call that, I've already downloaded it and already uncompressed it, because I've already ran this one before, so it happens straight away. And so path shows me where it is. Now in this case, path is dot, and the reason path is dot is because I've used this special base path attribute to path to tell it kind of like where's my starting point, you know, and that's used to print. So when I go here ls, which prints a list of files, these are all relative to where I actually unpath this to. So this just makes it a lot easier not to have to see the whole set of parent path folders. ls is actually, so path is a, see what kind of type it is. So it's a pathlib path object. Pathlib is part of the Python standard library. It's a really very nice library, but it doesn't actually have ls. Where there are libraries that we find super helpful, but they don't have exactly the things we want, we literally add the things we want to them. So we add ls. Okay. So if you want to find out what ls is, you know, as we mentioned, there's a few ways you can do it. You can put a question mark there, and that will show you where it comes from. So there's actually a library called FastCore, which is a lot of the foundational stuff in FastAI that is not dependent on PyTorch or Pandas or any of these big heavy libraries. So this is part of FastCore. And if you want to see exactly what it does, you can always remember, you can put in a second question mark to get source code. And as you can see, there's not much
Nice.
to it.
I love that.
And, you know, maybe most importantly, please don't forget about doc. Because really importantly, that gives you this show in docs link, which you can click on to get the documentation, to see examples, pictures if relevant, tutorials, guides, and so forth.
Love it.
So
Yeah, I want to get some hands-on practice on that as soon as I can. We're still in provisions mode, though. We've got to get to running.
So when you're looking at a new data set, you can kind of just I always start with this ls, see what's in it. And I can see here there's train folder, and there's a valid folder. That's pretty normal. So let's look at ls on the train folder, and it's got a folder called 7 and a folder called 3. And so this is looking quite a lot like our bear classifier data set. We downloaded each set of images into a folder based on what its label was. This is doing it at another level though. The first level of the folder hierarchy is it training or valid, and the second level is what's the label. And this is the most common way for image data sets to be distributed. So let's have a look. Let's just create something called trees that contains all of the contents of 3 directory, training, and let's just sort them so that this is consistent. Do the same for 7s, and let's look at the 3s, and you can see there's just numbered. Right. So let's grab one of those, open it, and take a look. Okay. So there's the picture of the 3, and so what is that really? Not 3. IM3. So PIL is the Python imaging library. It's the most popular library by far for working with images on Python. It's a PNG, not surprisingly. So Jupyter Notebook knows how to display many different types, and you can actually tell if you've got a new type, you can tell it how to display your type. And so PIL comes with something that will automatically display the image like so. What I'm going to do here, though, is to look at like how we're going to treat this as numbers. Okay? And so one easy way to treat things as numbers is to turn it into an array. So array is part of NumPy, which is the most popular array programming library for Python. And so if we pass our PIL image object to array, it just converts the image into a bunch of numbers. And the truth is, it's a bunch of numbers the whole time. It was actually stored as a bunch of numbers on disk. It's just that there's this magic thing in Jupyter that knows how to display those numbers on the screen. So when we say array, turning it back into a NumPy array.
Yeah, I know a little bit about that because I tinkered around with some code to try to look at juggling patterns. So I know a little bit about this. Not much though, that's for sure.
We're kind of removing this ability for Jupyter Notebook to know how to display it like a picture. But once I do this, we can then index into that array and create everything from the, grab all the rows from 4 up to not including 10, and all the columns from 4 up to not including 10, and here are some numbers. And they are 8-bit unsigned integers, so they are between 0 and 255. So an image, just like everything on a computer, is just a bunch of numbers, and therefore we can compute with it. We could do the same thing, but instead of saying array, we can say tensor. Now a tensor is basically the PyTorch version of a NumPy array. And so you can see it's exactly the same code as above, but I've just replaced array with tensor, and the output looks almost exactly the same, except it replaces array with tensor. And so you'll see this, that basically a PyTorch tensor and a NumPy array behave nearly identically, much, if not most of the time. But the key thing is that a PyTorch tensor can also be computed on a GPU, not just a CPU. So in our work, and in the book, in the notebooks, in our code, we tend to use tensors, PyTorch tensors, much more often than NumPy arrays, because they kind of have nearly all the benefits of NumPy arrays, plus all the benefits of GPU computation, and they've got a whole lot of extra functionality as well. A lot of people who have used Python for a long time always jump into NumPy because that's what they're used to. If that's you, you might want to start considering jumping into Tensor. Like wherever you used to write arrays, start writing Tensor, and just see what happens, because you might be surprised at how many things you can speed up or do more easily.
Yeah, that's definitely not me. I'm not the kind of guy who chooses NumPy over Tensor. I really haven't used NumPy that much. I might be using NumPy for my juggling project, where I could be using Tensor instead, but I haven't worked on that project in a long time. I kind of, now that I remember that, I'm kind of sad that I'm not working on that project right now. But let's just keep watching the video.
So let's grab that 3 image, turn it into a tensor. So that's going to be 3 image tensor. That's why I've got IM3. Okay. And let's grab a bit of it, okay, and turn it into a pandas data frame. And the only reason I'm turning it into a pandas data frame is that pandas has a very convenient thing called background gradient that turns a background into a gradient, as you can see.
Yeah, so this I kind of know about a bit about as well. I'm going to actually pull up that project because it looks like there's some parallels between that project, which is just a private project I did, and this project here. So it might be interesting to see the parallels between the two projects. So if I go back to my GitHub and then I go to Juggling Coach, we can see in my code here, Juggling Coach, we've got some code that changes the background gradient to black and white. Yeah, right here. So, oh God, I haven't looked at this in a long time. Wait, where is it? Here it is. So it's going to be, yeah, so, or wait, is this it? I haven't looked at this in a long time. So here's where we're changing it to black and white. So, yeah, unfortunately, it looks like there really aren't that many parallels between this coding project and the other one. We don't even have, we do have NumPy here. I'm kind of interested to see where I was using that. Nope, I haven't even used NumPy at all. Yep, so it's imported, but it's not even being used.
So here is the top bit of 3. You can see that the zeros are the whites.
And NumPy, he would be using Tensor instead of NumPy. You can use either or for the same purposes, but as he said, Tensor is a bit more optimized.
And the numbers get 255 at the plus. Okay, this one once it's in the middle of the circuit, great.
Okay, and now I have access to the notebook, so let's pull it up and see if we can follow along. I think this is going to be, so this is going to be notebook number 4. We're going to skip 3 for now. It's going to be MNIST basics. And then let's get down to this IM3_T line. And hopefully everything will run before then. So we're going to run this. And then we'll run the text boxes, but they won't do anything because they're just text. And then we'll run this line here. This line here. Keep running the lines. I did want to get practice. So let's comment this line out, create a new line, and then let's do doc path and run. Okay, so yep, now we've got the documentation, but we've got it for path. Let's see if we can get the documentation for something more useful. Okay, so now we've got, so now we've got it for path.ls. Yeah, and now we can see really good documentation, including the actual source code. So if we wanted to look at the source code without having to look at a new tab, however, I can do 2 question marks afterwards and hit run. And now we've got the source code just right here. Perfect. I love that so much. And then if I just want to do 1, I can see where the file is, go dig up the source code myself, or if I'm just confused, oh, where is this going to be? Oh, it's going to be in the utils. Yeah, really powerful self-help tools. I find the most important thing when it comes to becoming a professional with computers is asking good questions and getting the answers from your computer through pre-existing information. If you can do that, you're going to be invaluable as a computer professional. A lot of people, what they'll do is they'll come up with bad questions. You know, how do I do this, that, and then they'll ask a coworker. You know, kind of interrupting their focus, and you know, the coworker will just say, "Dude, put this in Google." Like, this is a really simple question you're asking that, you know, like a good example of this is, how do I exit from Vi? You know, that's the, I think it's the most Googled question ever. So how do I exit from Vi? Now, of course, I do understand, like, sometimes you should know that you're using Vi because you use Vim or whatever. So I realize sometimes it's hard to ask good questions, and depending on a person's experience level, that sort of thing, a good question can be what might be considered bad questions by somebody with more expertise and experience. So just because it's not the most profound, mind-blowing question in the world does not mean that it's not a good question. You can ask a brilliant question that would not seem brilliant in other contexts. So asking the right question is more important than asking good, profound, or interesting questions. Asking the right questions that can move you on your way and getting unstuck, that's the most important skill, I think. And then the second most important skill, or maybe even this might be more important than actually asking the question, is getting the answers from your computer, from pre-existing resources, not from living, breathing people. You want to get your answers from the computer some way, somehow. Your best source is the built-in documentation for something like this. If I want to learn something about path.ls, the first thing I would do is go like this, and then run this cell and go right to the doc. That's the number one most important thing. But even then, if I don't see it, asking a coworker, probably, yeah, that's probably the right thing to do. Just because they know what you're talking about, you're in the same context. But even then, to be honest, I would do one extra Google search, because there's an entire forum for this where they're going to have more information than your coworker or someone you're working with, like a friend or something, would have. And I personally think it's a little bit disruptive to be asking something of somebody else that you can just get yourself. And yes, I understand you've got to get along. You've got to kind of have candor, that sort of thing, morale. But I just think it's too inefficient. It takes too long to not do some initial research first, and to continually ask simple questions that can just be looked up. But that's kind of, I think that's consistent with what a lot of people in computer professionals believe, because it's like saying, you're a professional biker, but I'm not going to ride my bike, I'm going to walk. It's like, no, you have a bike, use the bike. Like, don't walk, like, ride your bike. It feels like the same way. Like, if you have a question, you have the internet, like, use it. So that's kind of what that's kind of a good analogy. Like asking a computer professional a simple question that you could have looked up yourself is like saying to is like if you were a professional bicyclist and you said to somebody, okay, I'm going to go down this hill, here, carry my bike while I walk. It's like, why am I doing this? Just ride your bike down the hill. What the hell? Like, yeah, if the bike's broken. So there are reasons, and then of course candor and morale. You've got to work together as a team. But I think a big part of that is kind of avoiding those pitfalls, because that is what a lot of computer professionals believe. And I'm actually not sure why I'm giving this rant here. This is more of a rant intended for my other topics. Well, actually no, because this is a part of my Gramps Networking Lessons channel. So if anyone's watching from my audience who watches my JNCIE SP courses, this is for you. All right, so let's continue on with the video.
So here we can see what's going on when our images into numbers actually get displayed on the screen.
Okay, and let's go down to that part. So I feel like I've gotten plenty of practice with the help, and I kind of went off on a bit too long of a rant, but we can see that's working. So let's try to get that picture that he has. So here we've got there, so then we've got the array, perfect. Yep, everything looks good. What picture does he have up that I don't have up? Okay, he's got like a chart. Let's see if we can get that chart. Aha, we got it, okay.
Just doing this. Okay. And so I'm just going to subset here. The actual full number in MNIST is a 28 by 28 pixel square, but that's 768 pixels. So that's super tiny, right? My mobile phone, I don't know how many megapixels it is, but it's millions of pixels. But it's nice to start with something simple and small. Okay. So here's our goal. Create a model. By model, it's some kind of computer program learned from data that can recognize threes as sevens. You can think of it as a 3 detector. Is it a 3? Because it's not a 3 system. So stop here, pause the video, and have a think. How would you do it? How would you, like, you don't need to know anything about neural networks or anything else. How might you, just with common sense, build a 3 detector?
Okay, so with common sense, how would you build a 3 detector? So, I mean, I would look for roundedness, and then I would make sure it had 3 points, and then I would make sure that it was just one continuous thing. It didn't have any separation. Like if you were looking for the letter I, that would be different. You would look for 2 different parts, but for the number 3, you only need 1 part. And then I would make sure that the 3 ends are on the left-hand side, because if it's the other way, that's not going to be a number 3. Number 3s are always read with the rounded parts to the right and the pointy parts to the left. I guess some variation of it being skewed, but if it were skewed all the way with the pointy parts up, that would be more of a W and not a 3.
Okay, so orthographic is a paper again. Got some notes down. I'll tell you the first idea that came into my head was, what if we grab every single 3 in the data set and take the average of the pixels? So what's the average of this pixel, 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 right? And so there'll be a 28 by 28 picture, which is the average of all of the 3s. And that would be like the ideal 3. And then we'll do the same for 7s. And then so when we then grab something from the validation set to classify it, they'll say like, oh, is this image closer to the ideal 3s, the ideal 3, the mean of the 3s, or the ideal 7? This is my idea. So,
oh man, that's like really triggering me to have interesting thoughts, because I would love to see an AI that had looked at handwriting, all kinds of handwriting, then handwrite itself what the ideal handwriting would look like. And then I would love to have my own handwriting trace that out so that my handwriting is just completely legible. Because when I was a kid, I learned cursive writing, and I don't know, I for pretty much my whole life, I wrote in nothing but cursive. I think I just wanted to kind of signal that I was a good student by doing that. But in my adult life, it's like, I can't read this. So I just started, now I write very clearly in print in a way that I can read very well. I think it does take me a little longer to write, but I can always go back and read exactly what I wrote. And I think that's more important. I would love to have that better though. So not only can I go back and read exactly what I wrote, I can go back and have it be really nice and clear and easy on the eyes.
I'm going to call this the pixel similarity approach. I'm describing this as a baseline. A baseline is like a super simple model that should be pretty easy to program from scratch with very little magic, maybe just a bunch of kind of simple averages, simple arithmetic, which you're super confident is going to be better than a random model, right? And one of the biggest mistakes I see in even experienced practitioners is that they fail to create a baseline. And so then they build some fancy Bayesian model or some fancy, they create some fancy Bayesian model or some fancy neural network, and they go, wow, Jeremy, look at my amazingly great model. And I'll say, like, how do you know it's amazingly great? They say, oh, look, accuracy is 80%. And then I'll say, okay, let's see what happens if we create a model where we always predict the mean. Oh, look, that's 85%. And people get pretty disheartened when they discover this, right? And so make sure you start with a very small baseline and then gradually build on top of it. So we need to get the average of the pixels. We're going to learn some nice Python programming tricks to do this. So the first thing we need to do is we need a list of all of the 7s. So remember, we've got the 7s. Which is just a list of file names, right? And so for each of those file names in the 7s, let's image.open that file, just like we did before in the PIL object, and let's convert that into a tensor. This thing here is called a list comprehension. So if you haven't seen this before, this is one of the most powerful and useful tools in Python. We've done something with C#, it's a little bit like LINQ, it's not as powerful as LINQ, this is somewhere right here. We've done some functional programming in JavaScript, so we have some of the things to do in that too. But basically, we're just going to go through this collection. Each item will become called O, and then it will be passed to this function, which opens it up and turns it into a tensor, and then it will be collated all back into a list. So this will be all of the 7s.
Okay, let's get that far in the code. Okay, worked for me.
Tensors. So Phil and I use linguistic dictionary comprehensions every day. And so you should definitely spend some time checking it out if you haven't already. So now that we've got a list of all of the trees as tensors, let's just grab one of them and display it. So remember, this is a tensor, not a PIL image object. So Jupyter doesn't know how to display it. So we have to use the command to display it and show the image as fast AI command that displays tensor. So here is the tree. So we need to get the average of all of those trees. So to get the average, the first thing we need to do is to change this so it's not a list, but it's a tensor itself. But currently, 3 tensors, 1 has a shape, which is 28 by 28. So this is the rows by columns, the size of this thing.
All right, so let's get that far. All right, I'll get down to the blurry 3.
Right? But 3 tensors itself
Oh, okay. I got a little bit far.
this is a list. So I can't really easily do mathematical computations on that. So what we could do is we could stack all of these 28 by 28 images on top of each other to create a 3D cube of images. And that's still called a tensor. So a tensor can have as many of these axes or dimensions as you like. And to stack them up, you use enough stack. Right? So this is going to turn the list into a tensor. And as you can see, the shape of it is now 6131 by 28 by 28. So it's kind of like a cube of height 6131 by 28 by 28. The other thing we want to do is if we're going to take the mean, we want to turn that into floating point values because we don't want to kind of have integers rounding off. The other thing to know is that it's just kind of a standard in computer vision that when you're working with floats, you expect them to be between 0 and 1. So we just divide by 255 because they were between 0 and 255 before. So this is a pretty standard way to kind of represent a bunch of images in PyTorch. So these 3 things here are called the axes: first axis, second axis, third axis. And overall, we would say that this is a rank 3 tensor. It has 3 axes. So this one here was a rank 2 tensor. So 2 axes. So you can get the rank of a tensor by just taking the length of the shape. 1, 2.
Okay, yeah, I think I did all that so far. Yep, so this is the cell. Okay.
3. Okay. You can also get that from the word, I've been using the word axis. You can also use the word dimension. I think NumPy tends to call axis, PyTorch tends to call dimension. So the rank is also the number of dimensions in Endian. So you need to make sure that you remember this word rank is the number of axes or dimensions in a tensor, and the shape is a list containing the size of each axis.
Okay, I remember that.
So we can now say stack tree.
Okay, so rank is the number of something, and I already forgot what the other one was. Stack? Or cube? I don't remember. I'm sure it'll be in the questions later.
Is dot mean. Now if we just say stack tree is dot mean, that returns a single number. That's the average pixel across that whole cube, the whole rank 3 tensor. But if we say mean 0, that is take the mean over this axis. That's the mean across the images. Right? And so that's now 28 by 28 again, because we kind of like reduced over this 6131 axis. We took the mean across that axis. And so we can show that image. Here it is, our ideal tree. So here's the ideals.
Oh, okay, that's cool. So these blurry images, which is kind of funny because they're kind of blurry, actually do show that thing I was interested in, which is what is the most ideal handwritten digit. So like if you're learning, if you were a young child learning handwriting, Now, maybe not necessarily these, but you can set this up. Well, not the young child is, but if you're lucky to have parents that can do this, or some sort of family friend or relative, you can generate the ideal images based on how everyone else in the world is writing, and then you can learn to write the images, or like write the digits that way.
Seven, using the same approach. Right. So now let's just grab a tree. Any old tree. Here it is. And what I'm going to do is I'm going to say, well, is this tree more similar to the perfect tree, or is it more similar to the perfect 7? And whichever one is more similar to, I'm going to assume that's the answer. So we can't just say, look at each pixel and say, what's the difference between this pixel, 0, 0 here, and 0, 0 here, and 0, 1 here, and 0, 1 here, and take an average. The reason we can't just take the average is that there's positives and negatives, and they're going to average out to nothing. Right? So I actually need more to be positive numbers. So there's two ways to make more positive numbers. I can take the absolute value, which simply means remove the minus signs. Okay? And then I can take the average of those. That's called the mean absolute difference, or L1 norm. Or I could take the square of each difference, and then take the mean of that, and then at the end I could take the square root, and kind of undoes the square root. And that's called the root mean square error, or L2. So let's have a look. Let's take a 3 and subtract from it the mean of the 3's. And take the absolute value, and take the mean, okay, call that the distance, using absolute value of 3 to a tree, and then there is a number, 0.1. Okay? So this is the mean absolute difference of L1 norm. So when you see a word like L1 norm, if you haven't seen it before, it may sound pretty fancy, but all these math terms that we see, you can turn them into a tiny bit of code. Right? Don't let the math bits fool you. They're often like, in code it's just very obvious. Whereas with math you just have to learn it. Or learn how to Google it.
Yeah.
So here's the same version of squaring. Take the difference, square it, take the mean, and then take the square root. Okay. So now we do the same thing for our 3. This time we'll compare it to the mean of the 7s. Right? So the distance from a 3 to the mean of the 3's, which is absolute, was 0.1. And the distance from a 3 to the mean of the 7s was 0.15. So it's closer to the mean of the 3's than it is to the mean of the 7s. So we've guessed therefore that this is 3, based on the mean absolute difference. Same thing with RMSE, root mean square error. We need to compare this value with this value. And again, root mean square error, it's closer to the mean 3 than to the mean 7. So this is like a machine learning model, and it's a data-driven model, which attempts to recognize 3's versus 7's. And so this is a good baseline. I mean, it's a reasonable baseline, it's going to be better than random. We don't actually have to write out minus apps mean. We can just actually use L1 loss. L1 loss does exactly that. We don't have to write minus squared. We can just write MSE loss. That doesn't do the square root by default, so you have to pump it. Okay. And as you can see, they're exactly the same numbers. It's very important before we kind of go too much further to make sure we're very comfortable working with arrays and tensors. And they're so similar. So we can start with a list of lists, right? Which is kind of a matrix. We can convert it into an array or into a tensor. We can display it, and then it'll almost the same. You can index it to a single row. You can index it to a single column. And so it's important to know, this is very important, column means every row, because I put it in the first spot. Right? So if I put it in the second spot, it would mean every column. And so therefore, comma colon is exactly the same as removing it. So it just turns out you can always remove columns at the end, because they're just implied. Right? You may not have to. And I often kind of put it in anyway, because it just kind of makes it a bit more obvious how these things kind of match up or how they differ. You can combine them together.
Yep, so it stands for column 1, everything in the row. And if you don't have it, it stands for everything in the row. So this is going to do all the columns, but only, or sorry, this is going to be row 1, everything in the column, right? Oh, no, this is going to be column 1, but everything in the, wait. Oh no, this is going to be row 1, everything in the row. So 4, 5, and 6, everything in row 1. And without this, it would do that by default. So this is going to be okay, everything in the first column. Wait, but shouldn't this be a 4 if that was the case? I'm confused.
It can be the first row, and everything from the first up to not including the third column.
Okay, so I think it's rows and columns. So the first row, I don't know. I'm confused.
You can add stuff to them, you can check their type. Notice that this is different to the Python. The Python type, the type is a function.
Right.
Just tells you it's a tensor. If you want to know what kind of tensor, you have to use type as a method. But it's a long tensor. You can modify it by float, turn it into a float. So have a feel around. If you haven't done much stuff with NumPy or PyTorch before, this is a good opportunity.
I haven't.
Go crazy, try things out. Try things that you think might not work and see if you actually get an error message.
Okay, so let's try to get an error message. So we're gonna just run everything the way you had it. Yep, so we've got the long tensor. Okay, so now let's go back and try to get an error message. So we'll try to, let's just put the number 2 here and see what we get. Okay, so we got 2 and 5. Let's do 2 colons. Okay, so it looks like we get the whole thing. So that kind of puts everything else in context then. So we can see this number 1, since we're getting the whole thing, we can see it's of course, because it starts at 0. So if I were to change this to 0, we're gonna get 1, 2, 3 because that's the 0 width. So yeah, he kind of was a little bit unclear when he said it was the first row, because it's actually going to be the second row. It's going to be the row at index 1, which is the second row. Okay, so then now let's make it more clear. Yep, so this first number is the rows, and if we don't, yep, so you can see we're getting rows. So the other thing we can do is say like that, and then we get the column, and same thing, index 1. So we're going to get the second column, and if I go 0, we're going to get 1 and 4. Yep, and then if I go 2, we'll get 3 and 6. Now, one thing that might be interesting that I think, there we go, that I can do is I can do -2, and we should get 6 and 3. Nope, so we get no, never mind, because this is an index from the, so it's 0, 1, wait, we're getting 2 and 5. Yeah, so we're getting from the end. So -1 would be this one, -2 would be this one here. So -1 would give us 3 and 6. Okay, perfect. So what I was meaning to do, you can do a double colon -1, and then I should get 6 and 3. Nope. This step must be greater than 0. Okay, so I guess I'm not sure how to do that then. But I did get an error message, which he wanted to see if we could get, and we did that, so let's keep going.
So we now want to find out how good is our model. our model that involves just comparing something to the mean. So we should not compare, we should not check how good our model is on the training set, as we discussed. We should check it on the validation set. And we already have a validation set. It's everything inside the valid directory. So let's go ahead and combine all those steps before. Let's go through everything in the validation set 3, ls, open them, turn them into a tensor, stack them all up. Turn them into floats, divide by 2 times. Okay? Let's do the same 7s. So we're just putting all the steps we did before into a couple of lines. I always try to print out shapes, all the time, because if the shape is not what you expected, then you can get weird things going on. But the idea is we want some function is 3 that will return true if we think something is 3. But to do that, we have to decide whether our digit that we're testing on is closer to the ideal 3 or the ideal 7. So let's create a little function that returns, takes the difference between two things, takes the absolute value, and then takes the mean. So we're going to create this function, and this distance, that takes the difference between two tensors, takes the rest of the value, and then takes the mean, and then takes the mean, and look at this, we've got minus this time. It takes the mean over the last, over the second last and third last. Sorry, the last and second last dimensions. So this is going to take the mean across the x and y axes. And so here you can see it's returning a single number, which is the distance of 3 from the mean 3. So that's the same as the value that we got over 1.11. So we need to do this for every image in the validation set, because we're trying to find the overall metric. Remember, the metric is the thing we look at to say how good is our model. So here's something crazy. We can call m the distance not just on R3, but on the entire validation set against the main 3. But that's wild. There's no normal programming that we would do where we could somehow pass in either a matrix or a rank 3 tensor, and somehow it works both times. And what actually happened here is that instead of returning a single number, it returned 1,010 numbers. And it did this because it used something called broadcasting. And broadcasting is like a super special magic trick that lets you make Python into a very, very high performance language. And in fact, if you do this broadcasting on GPU tensors of PyTorch, it actually does this operation on the GPU, even though you wrote it in Python. Here's what happens. Look here, this A minus B. So we're doing A minus B on two things. We've got, first of all, valid 3 tensor. Valid 3 tensor is 1,000 or so images. Right? Remember, the mean 3 is just our single ideal 3. So what is something of this shape minus something of this shape? Well, broadcasting means that if this shape doesn't match this shape, like if they did match, it would just subtract every corresponding item. But because they don't match, it actually acts as if there's 1,010 versions of this. So it's actually going to subtract this from every single one of these. Okay? So broadcasting, let's look at some examples. So broadcasting requires us to first of all understand the idea of element-wise operations. This is an element-wise operation. Here is a rank 1 tensor of size 3, and another rank 1 tensor of size 3. So we would say these sizes match, that's the same. And so when I add 1, 2, 3 to 1, 1, 1, I get back 2, 3, 4. It just takes the corresponding items and adds them together. That's called element-wise operations. So when I have different shapes, as we described before, what it ends up doing is basically copies this number 1,010 times. And it acts as if we said valid 3 tens minus 1,010 copies of mean 3. As it says here, it doesn't actually copy mean 3 1,010 times, it just pretends that it did. Right? It just acts as if it did. It's basically kind of loops back around to the start again. And it does the whole thing in C, or in CUDA on the GPU. So then we see absolute value. So let's go back up here. after we do the minus, we declare absolute value. But what happens when we call absolute value on something of size 10, 10 by 28 by 28? Just calls absolute value on each underlying thing. Okay. And then finally, we call mean. Minus 1 is the last element, always in Python. Minus 2 is the second last. This is taking the mean over the last two axes. And so then it's going to return just the first axis. So we're going to end up with 1010 means for 1010 distances, which is exactly what we want. We want to know how far away is each of our validation items away from the ideal tree. So then we can create our is3 function, which is, hey, is the distance between the number in question and the perfect tree less than the distance between the number in question and the perfect 7? If it is, it's a tree. Okay? So for R3, that's the actual tree we have, is it a tree? Yes. Okay. And then we can turn that into a float, and yes becomes 1. Thanks for broadcasting, we can do it for that entire set, right? So this is so cool. We basically get rid of loops. In this kind of programming, you should have very few loops. Loops make things much harder to read and hundreds of thousands of times slower. On the GPU, potentially tens of millions of times slower. But we can just say is3 on our whole valid tree tens, and then turn that into a float, and then pick the mean. So that's going to be the accuracy of the trees on average. And here's the accuracy of the 7s. It's just 1 minus that. So the accuracy across trees is about 91%. The accuracy on 7s is about 98%, and the average of those two is about 95%. So here we have a model that's 95% accurate at recognizing trees and 7s. It might surprise you that we can do that using nothing but arithmetic, right? So that's what I mean by getting a good baseline. Now, the thing is, it's not obvious how we kind of improve this, right? I mean, the thing is, it doesn't match Arthur Samuel's description of machine learning, right? This is not something where there's a function which has some parameters which we're testing against some kind of measure of fitness and then using that to like improve the parameters iteratively. It's one step, and that's that, okay? But we would try and do it in this way, where we arrange this automatic means of testing the effectiveness of a weight assignment, we call it a parameter assignment, in terms of performance, and a mechanism for altering the weight assignment and maximize the performance. We want to do it that way, right? Because we know from chapter 1, lesson 1, if we do it that way, we have this like magic box called machine learning. We can do, particularly combined with neural nets, to be able to solve any problem in theory. If you can at least find relative weights. So we need something that we can adapt better and better. So let's think about a function which has parameters. So instead of finding an ideal image and seeing how far away something is from the ideal image, so instead of like having something where we test how far away we are from the ideal image, what we could instead do is come up with a set of weights at each pixel. So we're trying to find out if something is another 3. And so we know that like in the places that you would expect to find 3 pixels, you could give those like high weights. So you can say, hey, if there's not in those places, you can give it like a high score. And if there's lots in other places, we'll give it like a low score. But we can actually come up with a function where the probability of something being say an 8 is equal to pixels in the image multiplied by some set of weights, and then we sum them up. Right? So then anywhere where the image we're looking at has pixels where there are high weights, it's going to end up with a high probability. But here S is the image that you're interested in. And we're just going to represent this as a vector. So let's just have all the rows stacked up end to end with a single line. So we're going to use an approach where we're going to start with a vector W. So vector is rank 1 tensor. Okay. We're going to start with vector W. That's going to contain random weights, random parameters, depending on whether you use the Samuel version of the terminology or not. And so we'll then predict whether a number appears to be a 3 or a 7 by using this tiny little function. And then we will figure out how good the model is, where we will calculate like how accurate it is or something like that. This is the loss. And then the key step is we're going to calculate the gradient. Now the gradient is something that measures in each weight. If I made it a little bit bigger, would the loss get better or worse? If I made it a little bit smaller, would the loss get better or worse? And so if we do that every weight, we can decide for every weight whether we should make that weight a bit bigger or a bit smaller. So that's called the gradient. Right? So once we have the gradient, we then step, that's the word we step, change all the weights up a little bit for the ones where the gradient which said we should be a bit higher, and down a little bit for the ones where the gradient said they should be a bit lower. So now, should be a tiny bit better. And then we're going to go back to step 2. And calculate a new set of predictions, using this formula. Calculate the gradient again. Step for weights. Keep doing that. So this is basically the flow chart. And then at some point, when we're waiting or when the loss gets good enough, we'll stop. So, these 7 steps, 1, 2, 3, 4, 5, 6, 7, these 7 steps are the key to training all deep learning models. The technique is called stochastic gradient descent. Well, it's called gradient descent. We'll see the stochastic very soon. And for each of these 7 steps, there's lots of choices around exactly how to do it. Right? We just kind of hand grade a lot. Like, what can random initialization? How do you calculate a gradient? Exactly what step do you take to a gradient? How do you decide this stuff? Blah, 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 right? So in this course, we're going to be like learning about these steps. That's kind of part 1. The other big part is like, well, what's the actual function? So how do we train the thing? What does it mean to train? So we initialize parameters with random values. We get some function that's going to be the loss function that will return a number that's small if the performance of the model is good. In some way to figure out whether the weight should be increased a bit or decreased a bit. And then we need to decide like when to stop, which would have saved us to a certain number of loss. So let's like go even simpler. Right? We're not even looking at this. We're going to start with this function x squared. Okay. And in fuzzy I we've written a tiny little thing called plot function and then plus the function. Right, so there's our function, f. And what we're going to do is we're going to try to find, this is our loss function, so we're going to try and find the bottom point. Right? So we're going to try and figure out what is the x value which is at the bottom. So our 7-step procedure requires us to start out by initializing. So we need to pick some value. Right? So the value we pick is this, let's just randomly pick -1.5. Great. So now we need to know if I increase x a bit, remember this is my loss. Does my loss get a bit better? Remember better is smaller or a bit worse. So we can do that easily enough. We can just try a slightly higher x and slightly lower x and see what happens. Right? And you can see it's just the slope. Right? The slope at this point tells you that if I increase x by a bit, then my loss will decrease. Because that is the slope at this point. So if we change our weight, our parameter, just a little bit in the direction of the slope, right? So here is the direction of the slope, and so here's the new value at that point, right? And then do it again, and then do it again. Eventually, we'll get to the bottom of this curve. Okay? So this idea goes all the way back to Isaac Newton, at the very least, and this basic idea is called Newton's method. So the key thing that you've got to do is calculate this slope. And the bad news is, do that in calculus. This is bad news for me, because I've never been a fan of calculus. We have to calculate the derivative. Here's the good news though. Maybe you spent ages in school learning how to calculate derivatives. You don't have to anymore. The computer does it for you. And the computer does it fast. It uses all of those methods that you learned in school, and a whole lot more, like clever tricks to speed them up, and it just does it all automatically. So for example, it knows, I don't know if you remember this from high school, that the derivative of x squared is 2x. It's just something it knows, it's part of its fix, right? So PyTorch knows that. PyTorch has an engine built in that can take derivatives, find the gradient of functions. So to do that, we start with a tensor, let's say, and in this case we're going to modify this tensor with a special method called required spread. And what this does is it tells PyTorch that any time I do a calculation with this xt, it should remember what calculation it does so that I can take the derivative later. You see the underscore again? An underscore at the end of a method in PyTorch means that this is called an in-place operation. It actually modifies this. So it requires grad underscore, modifies this tensor to tell PyTorch that we want to be calculating gradients on it. So that means it's just going to have to keep track of all of the computations we do so that it can calculate the derivative later. Okay, so we've got the number 3, and let's say we then call f on it, and then f is just squaring it. So 3 squared is 9. But the value is not just 9, it's 9 accompanied with the grad function, which is that it knows that the power operation has been taken. So we can now call special method backward. And backward, which refers to back propagation, which basically means take the derivative. And so once it does that, we can now look inside xt, because we said requires grad, and find out the gradient. And remember, the derivative of x squared is 2x. In this case, that is 3. 2 times 3 is 6. Right? So we didn't have to figure out the derivative. We just call backward and then get the grad attribute to get the derivative. So that's how easy it is to do calculus in PyTorch. So what you need to know about calculus is not how to take a derivative, but what it means. And what it means is it's a slope at some point.
Yep.
Now here's something interesting. Let's not just take 3, but let's take a rank 1 tensor, also known as a vector, 3, 4, 10. And let's add sum to our f functions. So we've got x squared dot sum. And now we can take f of this vector, get 125, and then we can say backward, and then grad, and look, 2x, 2x, 2x. Right? So we can calculate. This is vector calculus, right? We're getting the gradient for every element of the vector with the same 2 lines of code. So that's kind of all you need to know about calculus, right? And if this is this idea that the derivative for gradient as a slope is unfamiliar, check out Khan Academy. They have some great introductory calculus, and don't forget you can skip all the bits where they teach you how to calculate the gradient system. So now that we know how to calculate the gradient, that is the slope of the function, that tells us if we change our input a little bit, how will our output change correspondingly. That's what a slope is. Right? And so that tells us that every one of our parameters, if we know their gradients, then we know if we change that parameter up a bit or down a bit, how will it change our loss. So therefore, we then know how to change our parameters. So what we do is, let's say all of our weights are called W. We just subtract off them the gradients multiplied by some small number. And that small number is often a number between about 0.001 and 0.1. It's called the learning rate. Okay? And this here is the essence of gradient descent. So if you pick a learning rate that's very small, then you take the slope and you take a really small step in that direction. Another small step, another small step, another small step. And it's going to take forever to get to the end. If you pick a learning rate that's too big, you jump way too far each time. And again, it's going to take forever. And in fact, in this case, sorry, because we're assuming we're starting here, it's actually so big that it got worse and worse. Or here's one where we start here, and it's like, it's not so big it gets worse and worse, but it just takes a long time to balance them out. Right? So picking a good learning rate is really important, both in making sure that it's even possible to solve the problem, and that it's possible to solve it in a reasonable amount of time. So we'll be learning about how to pick learning rates in this course. So let's try this. Let's try using gradient descent. I said SGD was not quite accurate, it's using gradient descent to solve an actual problem. So the problem we're going to solve is, let's imagine you were watching a roller coaster go over the top of a hump, right? So as it comes out of the previous hill, it's going super fast, and it's going up the hill, and it's going slower and slower and slower. It goes to the top of the hump, and then it goes down the other side, it goes faster and faster and faster. So if you had a stopwatch or whatever, or some kind of speedometer, and you were measuring it just by hand at kind of equal time points, you might end up with something that looks a bit like this. Right? And so the way I did this was I just grabbed A range, just grabs the numbers from 0 up to 20. Right? So these are the time periods at which I'm taking my speed measurement. And then I've just got some quadratic function here, multiplied by 3, and then square it, add 1, whatever, right? And then I also, actually, sorry, I take my time, minus 9.5, square it, times 9.5, add 1, and then I add a random number to that. Or I add a random number to every observation. So I end up with a quadratic function, which is a bit lumpy. So this is kind of like what it might look like in real life, because my speedometer kind of testing is not perfect. Alright, so we want to create a function that estimates at any time what is the speed of the roller coaster. So we start by guessing what function it might be. So we guess that it's a function a times time squared plus b times time plus c. Remember from school, it's called a quadratic. So let's create a function, right? And so let's create it using kind of the Arthur-Samuels technique, machine learning technique. This function is going to take two things. It's going to take an input, which in this case is a time, and it's going to take some parameters. And the parameters are a, b, and c. So in Python, you can split out a list or a collection into its components, like so. And then here's that function. Okay. So we're not just trying to find any function in the world, we're just trying to find some function which is a quadratic by finding an a and a b and a c. So the Arthur-Samuel technique for doing this is to next up come up with a loss function, come up with a measurement of how good we are. So if we've got some predictions that come out of our function, and targets, which are these actual values, then we could just do the mean squared error. Okay, so here's that mean squared error. So the difference squared, okay, mean. So now we need to go through our 7-step process. We want to come up with a set of 3 parameters, a, b, and c, which are as good as possible. So step 1 is to initialize a, b, and c to random values. So this is how you get random values, 3 of them in PyTorch. And remember, we're going to be adjusting them, so we have to tell PyTorch that we want the radius. I'm just going to save those away so I can check them later. And then I calculate the predictions using that function, f, which is this. And then let's create a little function which just plots how good at this point are our predictions. So here is a function that prints in red our predictions, and in blue our targets. So that looks pretty terrible. So let's calculate the loss using an MSE function we wrote. Okay, so now we want to improve this. So calculate the gradients using the 2 steps we saw, call backward and then get grad. And this says that each of our parameters has a gradient that's negative. Let's pick a learning rate of 10 to the minus 5, or we multiply that by 10 to the minus 5. And step the weights. Remember, step the weights means minus equals learning rate times the gradient. There's one little trick here, which I've called dot data. The reason I've called dot data is dot data is a special attribute in PyTorch, which if you use it, then the gradient is not calculated. And we certainly wouldn't want the gradient to be calculated of the actual step we're doing. We only want the gradient to be calculated of our function f. Right? So when we step the weights, we have to use this special dot data attribute. After we do that, delete the gradients that we already had, and let's see if loss improved. So the loss before was 25,800, now it's 5,400. And the plot has gone from something that goes down to minus 300 to something that's much better. So let's do that a few times. So I just grab those previous lines of code and paste them all into a single cell. Okay, so creds, loss, backward data, creds, none. And then from time to time, print the loss out. And repeat that 10 times. And look, getting better and better. And so we can actually look at it getting better and better. So this is pretty cool, right? We have a technique. This is the Arthur-Samuel technique for finding a set of parameters that continuously improves by getting feedback from the result of measuring some loss function. So that was kind of the key step, right? This is the gradient descent method. So you should make sure to kind of go back and feel super comfortable with what's happened. And if you're not feeling comfortable, that's fine, right? It's been a while, or if you've never done this kind of gradient descent before, this might feel super unfamiliar. So kind of try to find the first cell in this notebook where you don't fully understand what it's doing. And then stop, figure it out. Like look at a few things going on, do some experiments, do some reading, so you understand that cell where you're stuck before you move forwards. So let's now apply this to MNIST. So for MNIST, we want to use this exact technique. And there's basically nothing extra we have to do, except one thing. We need a loss function. And the metric that we've been using is the error rate, or the accuracy. It's like how often are we correct, right? And that's the thing that we're actually trying to make good, our metric. But we've got a very serious problem, which is, remember, we need to calculate the gradient to figure out how we should change our parameters. The gradient is the slope, or the steepness, which you might remember from school is defined as rise over run. It's y mu minus y whole divided by x mu minus x whole. So the gradient is actually defined when x mu is very, very close to x whole, meaning the difference is very small. But think about it. Accuracy. If I change the parameter by a tiny, tiny, tiny amount, the accuracy might not change at all, because there might not be any 3 that we now predict as a 7, or any 7 that we now predict as a 3, because we changed the parameter by such a small amount. So it's possible, in fact certain, that the gradient is 0 at many places. And that means that our parameters aren't going to change at all, because learning rate times gradient is still 0 when the gradient is 0 for any learning rate. So this is why the loss function and the metric are not always the same thing. We can't use a metric as our loss if that metric has a gradient of 0. So we need something different. So we want to find something that kind of is pretty similar to the accuracy, in that, like, as the accuracy gets better, this ideal function we want gets better as well, but should not have a gradient of 0. So let's think about that function. Suppose we had 3 images. Actually, you know what? This is actually probably a good time to stop, because actually, you know, we've got to the point here where we understand gradient descent. We kind of know how to do it with a simple loss function. And I actually think before we start looking at the MNIST loss function, we should improve it, because we've got so much assignments to do for this week already. So we've got build your web application, and we've got go step through step through this notebook and make sure you fully understand it. So I actually think we should probably stop right here before we make things too crazy. So before I do, Rachel, are there any questions? Okay. Great. All right. Well, thanks everybody. I'm sorry for that last minute change of tack there, but I think this is going to make sense. So I hope you have a lot of fun with your web applications. Try and think of something that's really fun, really interesting. It doesn't have to be like important. It could just be some cute thing. We've had students before. A student that I think he said he had 16 different cousins, and he created something that would classify a photo based on which of his cousins, sort of like his fiancé in his family. You can come up with anything you like. But show off your application, and maybe have a look around at what iPad-Widgets can do, and try and come up with something that you think is pretty cool. All right, thanks everybody. I will see you next week.
Okay, yeah, so I've got an idea for one. I've got kind of I guess, I'm going to make this public on my GitHub, so I can't do anything too silly. I was thinking like I would make like a gaydar, like have 1,000 pictures of celebrities who identify as homosexual, and then 1,000 pictures of celebrities who don't identify as homosexual, and then you upload your photo, and you can see what category you belong into. But that's perhaps a bit too, it is probably not an appropriate thing to use to do, because employers will be looking at my site and watching this channel. So that's just kind of the first thing I thought of for some reason. But I think to kind of clean that up, something that might be a little bit more appropriate is to say, that same concept, but are you a movie star, or are you not a movie star? So what I could do is say celebrities who are considered attractive, and I can find many photos of that and build a database of that, and then I can say celebrities who are not considered attractive, build a database of that, and then you can upload your own photo, and you can see if you were a celebrity, would you be considered attractive or would you not be considered attractive? So let's try that. We're gonna go attractive celebrities, and of course we've got to answer the questions too. So here we go. So we've got the 50 sexiest celebrities of 2019. So we're gonna be pulling some photos of them. So so hopefully I'd like to get just the faces, something very so that you can just upload your own face. So maybe just let me do an example screenshot here. Yeah, just like from the very top of the eyebrows. So like, well, you know what I could do? I could say touching the top of the head down to touching the clavicle, like that, and then touching the one ear and touching the other ear, and then there we go. And then you upload your own where it touches the top of the head, touches the ears, touches the clavicle, and you can see if you would be one of the sexiest celebrities or one of the ugliest celebrities. So let's do ugliest celebrities. So now we should, so 50, the top 50 world's ugliest celebrities. So we got Caitlyn Jenner, we've got this person, I don't know who that is, I don't know who any of these people are. Lady Gaga, I'm kind of surprised, I didn't think she was ugly. Donald Trump is ugly. Okay, now here we go. Here's somebody who I think can own the ugly label and kind of use that for like as a part of their identity. Some of these people, I'm not sure if they can do that, but this person I think definitely can make a kind of a identity for themselves when it comes to being ugly. And it looks like that's exactly what this person did. They got a... Oh, well, actually, never mind. It looks like somebody just made an assessment about her. So I don't know what you think. It's all subjective. It's probably not a good idea to just call someone ugly or not ugly. It's really it really depends on what you want. If you want to associate with somebody who's ugly or not ugly, that's really none of my business. So one thing I noticed is this is the 50 world's ugliest, but the problem with that is we only have 11. So if I could get the remaining celebrities, that'd be great. Oh, it looks like I can get names. So if I have names, I can look up pictures. Oops, I might have just downloaded a virus. But I mean, it's IMDb. That's a real thing, right? I thought IMDb was pretty credible. Yeah, I think I downloaded virus because I don't see it anymore. Well, I mean, it's okay. I can reinstall my operating system if it gets too bad. All of my stuff is all on the cloud anyways. Yeah, I don't see any. I used to get like pop-ups from Windows. Yeah, I probably got something like that now. But let's try to find a better a list. So let's do 50 ugliest celebrities. Now this is only male. We're gonna need male and female. Now here's the feet. So we want more than just feet. We want faces. I mean, there's not that many. There's not that many ugly celebrities. So we'll do 50 ugliest people. I mean, this is exactly what I need, but for some reason, it's just not showing all of the entries. Yeah, it's only showing 11 of the 50. Yeah, so I don't know if it's just named wrong, but here we go. 50 of the ugliest people. So that's not. I mean, here we go. Ugliest actors and actresses. So. Oh, here we go. Here we go. Yeah, like I would think like Steve Buscemi would be on that list. You know, no offense to him, but yeah, like John C. Reilly. See, I personally think you can call someone ugly without it being an insult. Like, you know, John C. Reilly you know, he's a comedic actor, he's a character actor, you know, he's a comedian. You don't have to be attractive to be a comedian. Like, I don't necessarily think calling somebody ugly is necessarily an insult on its own. I think, depending on the context, yes, it can be very insulting. It can be meant as an insult. But I just wanted to be clear that the purpose of this is just to satisfy the criteria of the exercise. It's not to make any sort of assessment of people's physical appearance necessarily. This is really just the only thing I could quite come up with, and I'm hoping that the attractive list has some diversity in it. The same way we have here, we have Forrest Whitaker, and it looks like Vincent and Danny Trejo, classic actor. So I'm hoping we can get more of a representation. Whoopi Goldberg in the attractive list as well. Okay, so let's go with this. So we're gonna have, these are gonna be our 33 people for our ugly list. So we're gonna need our sexy list. So here we go. Yep, and it looks like we do have more of a representation. Yeah, we have a more diverse representation of people, because I don't want it to just be like, oh well, if you're Hispanic, if you're black, if you're white, you know, that's what determines whether you're ugly or not. But I don't think that's going to be the case, because we can see there is, of course, the data I choose. I'm only going to be doing 30 pictures. So I'm gonna leave. Oh, perfect. Okay, no, I can do 50 because I can do 48. Oh yes, and I can make self assessments too. Like, personally, a lot of sports stars and professional wrestlers, probably it's uncontroversial to say that they're ugly. So yeah, so I've let me just write down the names I'm going to use, and we're going to get 50 names. Okay, so we're going to do Kai Schultz, whoever that is. I have no idea who any of these actors are. Yep, this person, that person, that person. Yeah, I think this will be. Hopefully, this works here. Now, of course, we've got our ugly celebrities wearing hats, that sort of thing. So it might just say, oh, if you're wearing a hat, you're ugly. If you're not wearing a hat, you're not ugly. And then, of course, we might have, like, for example, he's not smiling. So maybe if he were smiling, what I'm saying is like, here's another example, somebody who's not smiling, where I bet you most of the attractive celebrities are smiling. So it might just detect whether or not you're smiling. But it actually looks like that's not true. A lot of the celebrities on the attractive list, for example, Tom Hardy, don't appear to be, I mean, kind of smiling in the eyes, but he's definitely not smiling at all. So he's kind of the perfect person to have in the attractive. But you can see here again, you know, he's got really nice hair. He's got really nice trimmed facial hair. Nice, you know, he's. You know, it might just, you know, he's got a full head of hair. Dennis Franz is balding, so, you know, there's people who are balding who are not necessarily ugly, so it might not. It might just say, oh, all bald people are ugly. So hopefully we can get someone who's bald. Yep. Okay. Perfect. So we do have. Somebody who's bald and wearing glasses, who is not considered ugly in this list. So definitely, and he's number 18. So that's perfect because we're gonna do about 30 pictures each. And I would like to have equal men and women. Oh yeah, Jason Momoa is like. Okay. This is gonna work. I think this is gonna work. So I'm gonna have 30 pictures. They're going to be pictures of men and pictures of women, 15 each, 15 men and 15 women, and then we're going to have a group of ugly and not ugly. So, yeah. Okay, yeah, so Beyonce would be in the not ugly, but Steve Buscemi would be in the ugly. Oh, am I on a new list right now? Oh, no. Oh, shoot, we're at the sexiest. Okay, well, I didn't want to go sexy, but okay, well, let's do sexy. Okay. We're going sexy and not sexy. So, if you were a celebrity, would you be on the sexiest or ugliest list? So this is the question. If you were a celebrity, would you be one of the sexiest celebrities or one of the ugliest? So we're gonna have a list ugliest, like this, and then we're gonna have female. And we'll try to have like equal representation. I personally like. It's just hard to say like, oh, we want to have equal race representation, because, you know, race is just kind of a it's just let's put it this way. I'm not sure if it's going to be possible to do that. And then Well, anyways, let's just build up the list, and then yeah, and then we'll go through the list, and we'll figure that out. So, yeah, we've got Rosie O'Donnell in there on the ugliest list. Sandra Bernhard, I don't know who that is. Sissy Spacek, oh, is that Kevin Spacek? Spacey? No, they're not related. Paula Jones, a victim? Is that, who's Paula Jones? Oh, I see, okay, she was, I don't know if she's a celebrity. But these would be this would be like a perfect photo or a photo like this. I mean, I could find attractive people in ugly photos, but I think this counts because she is a celebrity. Granted, it's not. See, we're just asking, if you were a celebrity, would you be one of the sexiest celebrities or one of the ugliest? So she is one of the ugliest celebrities according to this amiannoying.com list here. And not according to my own personal assessment. Yeah, like I want to get like Ron Perlman in there. Steve Buscemi would be perfect. I'm surprised he's not. I'm kind of surprised that Rule Paul is in there, because isn't his whole... I thought he was basically a celebrity because he's not ugly. Like he's a fashion. Like I'd be surprised that there was like a fashion icon in the ugly section. Okay, so we've got Danny DeVito. That's I think a good one. Pretty uncontroversial. As I said, I don't necessarily believe that the word ugly is always a bad word. In fact, I remember reading this really good book when I was younger and into tennis. It's called Winning Ugly, and one of the guys who won a Grand Slam and then went on to become one of the most successful juggling coaches, not juggling, tennis coaches ever. He wrote a book about how to win tennis matches without, the smoothest serve, the fastest serve, the best spin on your forehand, just with basic fundamental skills that really don't have any flair, don't have any style. Like if somebody saw you playing, they wouldn't even necessarily think you were a professional player, just because you look kind of ugly when you play. You don't have the flair and the style and everything that the other professionals have, but you have hidden secrets, or in your mind you have hidden techniques that you use to gain an advantage, mental techniques. You come prepared. You have all your things more. You take every match very, very seriously with the intent to win, whereas others who are more skilled than you might blow things off. And it was basically a book about how to win against people who are better than you. So it was kind of a fun book to read, but I don't think I took any of the lessons to heart. I guess the only lesson I kind of took to heart was just the importance of when you want to actually win something, of being prepared for it. Like if you're just doing something without the intent to win, like you don't need the right shoes, you don't need backup tennis racket. You don't need, you know, maybe like a nail clipper in case something happens. Like, you know, every little thing to be prepared for. But if you really are serious about wanting to win something, that's something you can do so that it's possible for you to beat somebody more skilled than you. Because if they did not do that and something happens and they're not prepared and you're prepared, for example, let's say the sun is really bad on the tennis court, you brought sunglasses, they didn't bring sunglasses, you can probably outplay this person who's better than you because you have sunglasses and they don't. So. Okay, so let's, I guess I'm not gonna know exactly who's male and who's female just by their names, but let's just go with celebrities that I recognize. So I think a really good one would be this professional basketball player. I'm gonna make sure that I recognize, that I have him on there. Yep, and we've got some more. I think we had John C. Reilly on here already. Let's see if he's on there. So John. Nope, there's no John on here. So I don't think any of these celebrities made it on there. So let's add all these celebrities as well to the list. And I'm going to pause the video, but I'll be back soon, and we'll keep building this celebrities list. And then once we have that, we'll go on Google and we'll pull images and we'll create an image database of celebrities, their faces from the top of their head down to let's just say the bottom of their chin, because that's going to be easier to keep consistent, and then to the edge of their ears, or the edge of their head if their head is tilted, or the edge of their hair, we'll say. So like for John C. Reilly, we'll get all of his hair down to his chin and then all the way here, so we'll have some extra space beyond his ear where we won't cut off the hair. And then I guess I'm not sure for hats, that's going to be interesting to deal with. But we'll try to get an equal number of people wearing hats as people not wearing hats. We'll try to make the images as similar to each other as possible. The only difference will be the actors used to create the database of images, and whether or not they are universally considered attractive or ugly. And I think it's, as I've said before, it's uncontroversial to consider some celebrities ugly and some attractive. There are people who kind of own that phrase, or own that and make it their own. So those are the kind of celebrities I definitely want. So somebody like Forrest Whitaker maybe isn't the best, because I don't know if he particularly wants to be known as somebody who's ugly, but Ron Perlman is kind of the perfect person to include there, because he plays a lot of villains. He played Hellboy, who's, you know, a son of the devil, somebody known for being ugly. So so. Oh, okay, there's two people named Vincent on here. Okay, Versace. I think Joan Rivers might be good. Iggy Pop would be, well, again, I don't know if Iggy Pop, then especially Joan Rivers, are particularly happy about, or would be particularly happy, or even the least bit okay with being on a top 50 ugliest actors list, or celebrities list. I kind of want to, for ethical purposes, stick to people who would be more okay with that. Like I think Danny Trejo would be good too, because he plays a lot of like villainous characters who you know, he makes his living playing ugly characters. So being called ugly probably isn't a huge insult for him, because he makes his money by portraying characters such as villains and stuff that are considered ugly. Yeah, and this guy too. Again, he's known for villainous. Yeah, due to his villainous physical appearance. So anyone known for a villainous physical appearance, I think for ethical reasons, I'd want to use them instead of somebody who kind of wouldn't be as okay with being on an ugly list. So I'll kind of just make that assessment myself, trim this list down, but I definitely want to just have the list, and then I definitely want to have the list of attractive people. That's what I'm going to do next. I'm going to create a list of attractive people, and then we're going to narrow down the list of ugly people. The first thing I'm going to do, I think, is just trim out the people I think that maybe might not be so happy with being on the list, because their characters, like for example Macaulay Culkin, like he's a child actor. I don't even think he's been in anything since he was a child. So just straight up coming out and calling him ugly is pretty damn rude, because he's not even in like he is only a celebrity for the work he did as a child, and in fact that work was, the reason he was in that role was because he was considered cute. So to just come up and say that he's ugly, especially when he's no longer in the public eye, I think is kind of rude. But for somebody like Donald Sutherland, who I think he plays villains, or is known for villainous adversarial roles, that's going to be an insult, not an insult, but it might be a bit of a compliment, because you're saying, oh, you played that bad guy so well, you looked so villainous, menacing, and ugly. I really liked your performance. Somebody like Louis Guzman, I think, is a good candidate. It is a really good candidate to keep on this list. Likewise, William Dafoe, he played the Goblin in Spider-Man, so he'd be a really good person to have on this list. Okay, so I'm gonna pause it, but I'll be right back, and we'll make a list of attractive people next. All right, I am back. So the next part is going to be attractive celebrities. So we're going to go with the list we found here. So we're going to start with the most attractive, and we're just going to write down their names. Now, it would be really funny if we got one of the attractive celebrities on one of the ugliest celebrities list. I would love that. That would be amazing. Okay, so Kylie Jenner is the most attractive celebrity. The second most attractive celebrity is Jennifer Lopez. Okay, then we've got Kim Kardashian. All right, so who now we've only got females so far. So okay, we've got a male now. We've got David Beckham. So we definitely don't want the model to just say whether you're male or female and decide whether you're attractive just on account of that. So that's good that we're now getting both male and female. But similarly, we don't want the model to just say, "Oh, you're light skinned, so you're attractive." So we're gonna try to have the photos of people be as similar as possible. And a really good thing the model could do as well is to just turn the photo, just take the color out of the photo somehow. But even then, you would have different tones. I don't know who this person is. Yeah, I've never seen Creed 2. Because I always like, for me, Michael Jordan is a person, and I hear people say Michael Jeffrey Jordan a lot. I'm like, why are people saying that? It's probably because Michael B. Jordan is becoming so famous that you've got to say Michael J. Jordan, or else people will think you're talking about Michael B. Jordan now. Okay, so, yep, this looks good. Now we've got 50 people on this list. On this list we've got 78, so we're going to need to bring that list down a bit. But 50 should be fine. The other list only had 35, and everything seemed to be doing fine. So 50 should work fine. This one might not work because she's wearing special goggles there, but that can be one of the Oh, but the other thing to say, I'm not going to be using these photos here that you see here. I'm just going to be taking the names, Googling them, and I'm going to be finding like a really good picture I can use to kind of keep my database of pictures more consistent. So like this one looks really good because I can consistently, yep. So that should work. Haley Baldwin, good for you. You're on the attractive list, as is Tom Hardy. I'm 35. I don't know who any of these. Rihanna, I know who Rihanna is. I guess I'm not that old. And Adam Levine, I know as well. And that song, This Love, is actually an okay song too. One of the many songs I had to endure when I was younger. But actually one of the easier ones to endure. There were a lot of songs that I did not like because I was a classical musician, and I actually had a little bit of a kind of a bad attitude, I think, towards a lot of music, kind of thinking that it just wasn't complex enough, or it was just too repetitive, or it just kind of fell short from like classical music or like orchestral music or stuff like that. I kind of changed my tune a little bit. I like a lot of kind of like EDM stuff because I think the timbres in an orchestra are of course limited to woodwinds and strings and stuff. So I think really good electronic music has more complex timbres and a more variety of timbres, so the different kinds of sounds, and that kind of stuff I really enjoy. I really don't enjoy EDM electronic dance music that uses fart sounds for timbres. It seems like a lot of them do that, and I wish I could just like not have those somehow, or take out the a really good example of this is a really old school artist, but it's called Nero, Nero, by Aphex Twin. It like starts with this just absolutely beautiful thing, and then there's like a fart sound. It's like, what do you do? And like spitting sounds. It's like, what? Like, why? That's kind of why I'm actually pretty interested in trying to make some of that music myself, but it's just not what I do. I'm a network engineer by day, juggler at night, so it's like there's only so much time in the day. And apparently now I'm into AI as well, so Okay, so our attractive person list is going to be shorter than our ugly person list, which might say something about the society we're in. But we're going to count the number of male and female celebrities in the attractive list, and we'll use that to change our ugly list. And this is a really good one. We're definitely going to have Kit Harington in there because you can see he's actually frowning and scowling, kind of the same facial expressions that are used by some of the people on the ugly list. So we'll definitely try to find that sort of photo. Okay, so Olivia Munn is the least sexy celebrity, but congratulations, she is a sexy celebrity, not on the ugly list. So, yep. So the next step we're going to do is we're going to look at this list. We're going to sort it male and female. So anytime I see a female, I will move the name up. So yep, we've got Emily and Kendall. So they are both female. They go up. Okay, and then we've got Nick is male. Jenna, Vanessa, Bella, those are female. So we'll put them up here. Okay, and then we've got Michael is male. We've got Megan Fox. Channing, that's one I'm not super familiar with. I'm pretty sure it's male, but Zayn Malik, I have no idea. I'll have to look up that celebrity. Some of these names I won't be able to tell if they're male or female just by the name alone. Now I do have a feeling we'll have more female than male. Okay, so he's definitely male as far as I can tell. Yep. So here's a picture of him. He is male. This is probably the picture we'll use in the data set. Maybe this one. This one, I guess, I kind of like this one because the hair isn't such a prominent feature of it. It has more of like his, well, these have facial features as well, but he is definitely male, so he belongs on this bottom one. So Haley Baldwin belongs up here. Tom Hardy, Rihanna. Okay, so here's one where I can't tell just based on the name, and even Jamie I can't tell either. So we'll okay. So this is female. She goes to the top. Okay, and now Jamie. I'm not sure. Oops, I had a duplicate entry. So Jamie can be a boy or a girl's name. I think typically is a boy's name. Yes. Okay, Scott, Chris, those are easy ones. Jason, yep. Yep. So Jessica. Yeah, I'm pretty sure Liam is a boy's name, but I'm just gonna make sure. Yep. Okay. Okay, and then Selena. Here's one where I don't know. Idris. I guess it looks like it would be a girl's name, but let's Google it. Oh, okay. Yep. So this is a boy's name. Perfect. So now we're gonna need Ryan Reynolds to be the boy's name stuff. Yep. I know who this is. She is. Yep. Perfect. Okay, and Zac Efron, of course. Now Gabrielle. Oh no, this is a girl's name, of course. This one, Jesse Williams. I think Jesse is a gender-neutral first name. Yep, and it happens to be male. Okay, and Gabrielle Union. I'm pretty sure that is female. Yep. Perfect. Okay. And then Beyonce, female, of course. Henry Cavill. That's male, but I'm just wondering. Oh, okay. Yeah, I've just never heard of some of these celebrities, so I'm just curious if I would have recognized that person. Okay, so Justin Timberlake, yep, I know who that is. Ricky Martin, yep. Kourtney Kardashian, that's a female name. Okay, Chris Pine, Chris, that's got to be a male name. Camilla, I'm pretty sure that's female, but we'll Google it. Yes, okay, perfect. Yep, and these would be really good photos. Yep, Camila Cabello, yep, and then Khloe Kardashian, Cardi B, yep, both of those are female. And then we've got one more, Olivia Munn, she's going to be female as well. Okay, so the good news is it looks like the list made it pretty easy. We've got 50 celebrities, we've got 25 female, and we've also got 25 male. So yeah, we're good to go, I think. Now let's see how many male and female we have for ugly celebrities. So Aerosmith is a band. I'm going to take them out. So now we have even less. Oh, actually, we have 77. So we actually have more of these celebrities. But let's just separate the list out by male and female. So Tracy is female. Dwight sounds male to me. We will see. Yep, Dwight is definitely male. Carrot Top, I know who that is. Marty Feldman. So Joan Rivers. Yep. Yoko Ono, female. Kelsey Grammer's male. Rosie O'Donnell's female. Let's take a look at Rosie O'Donnell. Okay. Sarah, yep, Sarah's going to be female. Sissy, Paula, Bet, Ellen, Marge. And then I think Rhea Perlman. Yep, Rhea Perlman is female. Okay, RuPaul is kind of neither. I don't know if he's, well, I think RuPaul is one we can take off the list because he's he makes his life doing fashion and looking good. So to have him be on a ugly list just seems kind of rude to me. And we've got too many people on this list anyway. So I'm taking RuPaul off of there. He makes his money through fashion and looking good, so I don't think it's appropriate to have him on an ugly list. Michael Richards, though, Kramer from Seinfeld, perfect person for this list. Danny DeVito, Janet Reno, really good for the list as well. Politicians, I think, can be. I don't think you need to be as careful with being polite to a politician necessarily, because they're supposed to be representing you. And if they're not doing that, then, well, I don't know. I think you should be, by default, kind to everyone you meet. And even if there's reason not to be, instead of being rude, I think you're better just trying to distance yourself. I'm surprised that Martha Stewart made it on the ugly list, because Martha Stewart actually started her career as a model. You can see here's a photo of a young Martha Stewart, and she very much looks like a model. And even in her older age, I kind of have trouble understanding why she would be on this list, and it actually might throw out the model. So you know what, we're gonna take out Martha Stewart, because I don't think she's really meant for this list. She actually did work as a model. She's kind of known for trying to look good. So I don't think it's appropriate to have her on that list. Whoever made that list probably didn't do it objectively. They probably just put celebrities they didn't like on the ugly list. And I think there's justification for that with the insider trading. You know, maybe she's not ugly on the outside, but breaking the law is pretty ugly. Oh, yeah, this guy's the perfect candidate for this list. Okay, so here's Tammy Faye. She's got 4 names. I'm not sure who this is, or maybe this is 2 people. Nope, she's got 4 names. So yeah, this would be a great photo for it. Scottie Pippen. I'm kind of surprised Scottie Pippen is on this list. Like, some of the, like, NBA, well, now, okay, yeah, this would be a good photo for it. I guess when you're playing sports, like, ugly photos are pretty abundant. Okay, so Kai Schultz. Oh, this is a man. So he belongs. I thought that was a female name. Okay, this one I can't tell. Bodie, is that male or female? We'll see. It looks like they're actually twins. So we're gonna remove one of them. This looks like a decent photo to include. Let's see what the photos of Kai look like. Okay, so I want to say the photos of Kai are going to be better to include, especially a photo like this, because he's smiling, and I don't want it to just detect whether the person is smiling or not. So it'll be important to have some photos in there of people smiling. Okay, so now we've got Steve Buscemi, perfect. Marilyn Manson, really good. John C. Reilly, perfect. Tori Spelling is going to be on the female list. Now we've already got 25 females on here, and we've got 25 males. Let's just go ahead and finish this sorting, and that way, if I feel like it's unethical to have someone on here, I can remove them and still have all the data I need. And of course, this is not a very the consequences of mistakenly adding someone, I don't think are going to be huge. I mean, maybe there's a butterfly effect. They'll see my YouTube channel and watch the whole thing and get depressed and start a civil war in the USA. But I doubt that will happen. So Vincent. Okay. Let's see if this is okay. So this is a man. All right, let's see who this is. Yeah, this would be a good photo because this you kind of can't tell. It looks like he probably could be considered attractive. Oh, you know what? This isn't a celebrity. Yeah, I think we're talking about. Oh, are we talking about the Doctor Who guy? Yeah, I don't think we're getting a celebrity when we search for this Vincent. So we're gonna take him out, and we're gonna search for this other one. Because that person's just a random guy. Ah, okay, yeah. So this looks better. Oh, Versace. So this is female, female, female. Yep, and then Iggy Pop is male, female, male. Yep, Tilda is female, so Iggy Pop is male, William Dafoe male, Danny, Luis. Yep, these are all male. Linda Hunt is going to be female. Yep, and then Richard Keel, male. Haley Joel Osment, male. Whoopi Goldberg, female. Okay, Jesse Tyler Ferguson. I'm guessing that's a female. Nope, that's a male. Macaulay Culkin. And here's another one. You know, as I said, I don't think it's ethical to have him on here. You know, he was a child actor. He was known for being an adorable child actor, and now I haven't seen him in any sort of movie, anything like that in the public eye. So just to straight up out of nowhere say that he's ugly it seems a little unethical to me. Okay, Lawrence Fishburne. He's not known for playing attractive roles, so he's going to be a good one to include on there, I think. Sydney Potter. Now, Sydney, I do know a male named Sydney. Yep, so Sydney can be a male name. Okay, so now we've got extras. Yeah, I'm not sure who to take off right now. Let's go ahead and gather our pictures for our database. So to do that, I'm gonna open up my so my Fast AI course here, and then we're gonna say, oops, oh, here's the thing I downloaded. So I just downloaded it to a strange file. Let's see what this, okay, yeah, so whoops, we had we had everything ready to go for us to use in an easier manner. But we'll just do it. So we'll say celebrity my celebrity AI. Okay, so we're gonna have ugly, and we're gonna have attractive. We're gonna have sexy, and then we'll let's just call it attractive because this might be seen by employers. And then we'll say ugly. Okay, so let's start with the ugly, and then if there's ones that we want to remove, we'll do that. You know what? Let's start with the attractive, because then we can see, we've got too many images that are the same in the attractive. So we'll have more leeway if we start with attractive, because we want to trim away the extra entries in ugly so that the data aligns better with the data in attractive. So let's do that. So we're going to start with Kylie Jenner. and she's going to be in the attracted list. Okay, so let's get a good photo of Kylie Jenner. Okay, I think I want to go with this one. You know what? No, this one looks better. This one actually looks pretty good too. But you know, I'm trying to get that good frame so that I can take a picture. This one actually looks really good. Let's go with this one of Kylie Jenner. Okay, so we're gonna open this in a new tab. Yep, and then we're going to take a screenshot of it, and it's gonna be cutting off her head a little bit, so not quite ideal, but we'll go there like this, and then we'll stop a little bit. Yeah, so this will be the photo we'll use. So we're gonna save that. We're gonna add it to my desktop, Fast AI course, my celebrity AI, attractive, and then we'll call it 1. Okay. All right, so now let's get number 2, which is gonna be Jennifer Lopez. Okay, so I guess this one looks pretty good. Yeah, let's go with this one. Oops, and I'd like to get perhaps a bigger photo. Maybe this one's better. Yeah, let's go with this one instead. Yeah, this one looks perfect. Okay, so this one should be good. We're gonna save this. I'm gonna call it 2. Okay, so Kim Kardashian is gonna be next. All right, this will be a good one. All right, so right at the top of the hairline, and then just under the chin, kind of aligning with the ears. There we go. This will be 3. Okay, Kendall Jenner is next. Let's go with this one because the hair is kind of similar to the other ones. So yeah, this one looks good. So open image in new tab. Okay, and then we're gonna do, yep. Okay. So we're gonna go for 25 of these. So this is number 4. Oh my god, and this is gonna take a long time. And I don't even know if it's gonna work. Okay, so this is our next person, Aha. We'll go with this one. Okay, so we're gonna go with 5. All right, number 6. I guess this one looks good. Yeah, this one's good. Okay, so right above the head and right in line with the ears, perfect. Under the chin a little bit. This is going to be number 6. Okay. Now we need number 7, Vanessa Hudgens. Okay, well this is interesting. I guess this one is more similar to the other photos we've taken. But this one, I guess I'm gonna go with this one. Or you know what? Let's go with this one. Yeah, it looks a bit different in some ways. Well, I don't know. They all look the same so far. I don't think there's any blonde-haired actresses yet. Oh no, there is one. Okay, good. So we do have a bit of a variation in our data here. Okay, so that's number 7. So number 8. Alright, so here's attractive celebrity number 8. Looks like the first pick is going to be fine. Yep, that'll be good. Okay, number 9, let's go with this photo. And here we can see we've got a different hairstyle, not parted in the middle. Alright, so this is going to be number 9. We've got quite a few more to go. I'm not sure if I'll be able to finish this because this seems to have taken me a long time. Here's kind of the classic photo of Scarlett Johansson. Okay. So this is number 10. Now we can see here that none of them are wearing hats so far. So it might just tell us whether somebody's wearing a hat or not. So in our ugly celebrities list, we might want to just get rid of, not use any photos where somebody's wearing a hat. We also have seen that a lot of them have had black hair. So let's get this photo here, where she's using, and let's actually get a photo where she's not smiling. Although I can't remember if any of them are smiling. I guess this one looks good. Okay, let's go with this. Yeah, this will be good for our data set. Okay. Bam. Okay, go. So she is in the attractive celebrity list. Perfect. Okay, now we've got Hailey Baldwin next. Oh my god, this is just awful. I'm not enjoying this, but I want to get this to work because I think it will be interesting. Oops, so I gotta save it. Okay, and this is number 12. I mean, I can just use 15 instead of 25. I don't know. I think I'm getting it to work here. Okay, so next up is Rihanna. Google Images. Let's go with okay, yeah, let's go with this one. I mean, usually the first image is probably one of the better ones. And it's more of a more blurry pic too, so this is number 13. Yeah, it looks like we've got a lot of pics of people smiling. Not many of frowning, any of that sort of thing. So we should definitely for this next one include that because an attractive person frowning. But she doesn't look like somebody who frowns very much. I guess she's not smiling here. There we go. Okay. That's number 14. Okay, number 15. Okay, this one looks good. Use this. Okay. All right, we're getting there. We're getting to the end of the list. We're going to have 4 more to go. But this, I think, only took like 15 minutes, so should be able to do it in an hour. Oh man, for some reason, I usually let my apartment get a bit hotter, kind of later in the evening, and then I have it cool off. But the heat is like getting to me pretty badly right now. Oh, you know what? I have a I have a long sleeve shirt on that I could exchange for a short sleeve shirt, but I do have the sleeves rolled up. Oops, we won't put that in there, otherwise that would take us out of the Google image search. So now we've got the Gabrielle Union. Yeah, let's just do like the, well, let's do this one here. Yep, so we'll have kind of another blurry one. I can't remember what the last blurry one looked like. But I don't think it really matters that much if they're blurry. Well, let's see what the last blurry. Okay, the last blurry one was Rihanna. Yeah, okay, this will be fine, I think.
Okay, let's go with Beyonce. Okay, so I have not seen this picture of Beyonce before. We're using it. We're definitely using this one. Okay, so we're getting there. We're just got 6 more left. Okay, so yeah, let's go with plenty of non-smiling pics, which is good. Going to give us some more, because I don't want it to say that you are going to be a sexy celebrity or you're going to be pigeonholed into villainous roles based on whether or not you're smiling. Okay, so yep, we'll go with this one for Kourtney Kardashian. Oh, God damn it, this really sucks. I hate doing this. And I'm not feeling like faint or anything like that, but I'm feeling like I could feel faint if like I don't feel like sick or anything, but I feel like I could easily feel sick at some point. So I don't know if anyone can relate to that, but it's like where you don't feel like you're sick, but you feel like if you don't do something about how you feel, you might become sick. Okay, so 21, this is going to be 22. Okay, so almost there. We've just got Khloe Kardashian, Cardi B, and Olivia Munn. So here's Khloe Kardashian. Let's go with this photo. Okay, so 23. All right, and then Cardi B, and then just one more. This one looks good because it's a kind of a strange facial expression, quite a bit different than the other ones we've seen. Yeah, because we can see the other kind of all have similar facial expressions. Okay, so now the last one is going to be Olivia Munn. All right, so yep, let's go with this one. Okay, so hopefully this is gonna work. I have no idea. I've got a lot more work to do to gather those other images up. But let's do that. So the first celebrity is gonna be David Beckham. He's gonna be our number 26.
Okay, yeah, it feels a little bit better to sit down, but mostly it's just so unbearably hot in here. What's the temperature? It's only 86. It's not even hotter than it usually is. Okay, so now let's go with let's go with this photo. Okay. There we go. He's our number 26. All right, and then 27 is going to be Chris Hemsworth. So here we're going to have beards, non-beards. It's going to be probably a bit more. Each photo will probably be a little bit different because of that. A little bit more different than it would have been for the female photos. Okay, so 27. Nick Jonas. Okay, we'll go with, let's go with this one. Yeah, because his head isn't cut off. There's plenty of room to get the chin. Here I might miss it, so. That's what I'm looking for. That's why I will sometimes pick one image over the other, because it's just easier for me to get a screenshot of it. That's kind of what I'm optimizing for. So he's number 28. Oh my god, and we're going to 50. I don't know if I can make it. Yeah, I don't know if I can get to 50, and I'm probably not going to finish the questions. Okay, we'll use this one. Okay, perfect. Yeah, I don't know if I can get to I could probably get this done, but the ugly celebrities, like that's just gonna, it's already, this is taking me, I'm at the 3.5 hour mark right now. All right, let's go with this photo of Channing Tatum. But yeah, I've spent like probably more than 15 hours, more than 10 hours easily. But I've spent a lot of hours on this machine learning. All right, Chris Evans. I think he's an Avengers guy. I think I've heard of him before. Nope. No. We're not going to click the not safe for work one. This looks really good. Let's go with this one. Yeah, it's kind of a blurrier one, which I think is fine. Okay, so now we've got Zion. So that's a male name I found out recently. Found that out today. Found it out just now. Okay. So, yeah, let's go with this photo here. Perfect. It's working so well. Everything is working. Oh man, except for my feeling normal. I'm just too hot right now. I just feel like way too hot. At least I'm not like, because when I've gotten heat stroke before. I mean, I'm in Texas. or not heat stroke, but heat exhaustion. And what happens is I start to kind of fade out a little bit, and then I start to see double vision. And at that point, it's like, if I'm seeing double vision, like I'm having serious like heat exhaustion problems. Probably gonna go into like heat stroke or something if I don't somehow get a little bit cooler. So you know what? I think I'm gonna get an ice pack. Not because I'm seeing double or anything serious like that. Just because I feel so so incredibly hot right now. I think an ice pack will cool me off. So I'm gonna pause it, and when I come back, we'll do Adam Levine. Alright, I am back. I don't know why I felt so overwhelmingly hot just now, but I do have an ice pack here, so I'm just going to apply this to my forehead. Okay, yeah, oh, okay, yeah, that feels a lot better. I did get some sun today, so the sunburn usually I feel kind of strange when I get a sunburn, so that might be all that's going on. Okay, so let's move on to the next celebrity. Let's go with Adam Levine. Yep, I'm kind of excited about this photo because this is the look I tried to pull off in this abomination. I didn't quite get there, but I didn't. In my mind, I really didn't have kind of a finished picture of like what I would be okay looking like in doing this, and I think that I finally found it. Like, this is kind of what I was going for, and I don't think I hit it, but I think the reason I didn't hit it is I just didn't have the goal in sight. My beard was a little bit too long, but I mean, other than that, I was pretty close. I need to take it off the lip some more. But yeah, I just need to get that beard shorter, get it off the lip, and then I need to be blessed with unusually good looks, or get plastic surgery. But I think instead of that, I will continue to work on this course. Okay, so the next celebrity is going to be this person, whoever this is. I have no idea. Okay, so 35. Oh my god, this is such a nightmare. Scott Eastwood. Okay. Yeah, let's go with this. Yeah, I can't drink any more liquids tonight too. But it'd be nice to have some like cold water. I've only used my ice pack once though. I'll use it some more. Oh my god. Yeah, that's a good idea. Oh, I don't know why I got so hot. Oh, I didn't finish my drink. Alright, so he's going to be number 36. Okay, so let's move on to number 37. Chris Pratt. Whoever that is, I think Captain America. Yeah, I've heard of him. I think he was like Captain America or Thor or something. I don't even know. Yep, I think this will be a good photo. See what I think I do know who Chris Pratt is. I think he's the guy who like he used to play like a nerdy character in the show The Office, and then he became a superhero. So that's kind of good news for somebody like me who like has never been in shape. Yeah, Jason Momoa, like forget it, man. I'll never like if there are only people like Jason Momoa out there, I would not be optimistic about being able to get in better shape. Because he's just a specimen. But somebody like Chris Pratt, from what I understand, used to be was not always in shape. Okay, so next is going to be Liam Hemsworth, number 39. Okay, and we still don't have any hats. So in our ugly set, let's just avoid hats if we can. Okay, he's number 39. Hopefully I saved Momoa. I did, so we've got 39. Okay, so after this next one, I'll have 10 left. Ryan Reynolds, that'll be my... I'll have 10 left, starting with him, so... Okay, so this person's on the attractive list. Let's get this one. Yep, so this one will be easy to capture. Okay, so number 40. Let's go with this photo. I'm not sure. In case anyone hasn't figured it out yet, I have no idea what I'm doing. I don't know if this is going to work. I don't know if there's a better way to get this, a more automated way to get my data set, but I'm generally of the opinion that if you can do it, it's slow, it sucks, but it'll work. That's okay. Like it's really the end result that matters, not the method that gets you there. Alright, I need my ice pack again. Oh my god. Yeah, that was a huge difference maker. I was not... Oh yeah, my back, my neck too. Oh yeah. Oh, that was missing from my life. I'm back. So, yep, Zac Efron's number 42, so let's go on to number 43. So that's going to be Jesse Williams, whoever that is. I have no clue. He's a doctor, apparently. Oh, he's on Grey's Anatomy. I don't know. Okay, 43. Oh, here's Superman. So let's get this will be a good one of Superman. I didn't know Superman had a mustache though. I also thought Superman was like Shaquille O'Neal or Dwight Howard or Giannis Antetokounmpo, my favorite from Milwaukee because I grew up in Wisconsin. Okay, Timberlake is one of the attractive people, so let's get a good photo of him. Now we don't have any like side-facing photos, anything like that. But we can request not to have. Okay, this one I think looks like the best. Dude, I don't understand celebridom or whatever, being a celebrity. Like, why is he a celebrity? I guess he made music? That's like better than others? I guess? Why are any of these people celebrities? I guess they're in films? But like, is that like why is it worth so much? Like, why is being in a film something that you would pay somebody millions of dollars with and worship them for? Like, I just don't get it. Like, what about the person who, like, I don't know. I just don't get it. The whole concept of it. Okay, so now let's go 46. Okay, so we're almost done. We're just gonna have the ugly list. And then of course we'll have all the code, all that afterwards, so kind of a nightmare. But it seems to be going pretty well. Okay, so we're gonna have him on the attractive list. Living La Vida Loca. Okay, we've got two more left, number 49 and number 50. Oh my god, I am still not feeling it. Okay, let's get a kind of a broody image. Yep, that looks good. Okay, one more and this nightmare will come to an end. Final celebrity is going to be Ryan Gosling. Okay.
Okay, so we've got number 50. So now we've got to look at the ugly celebrity list. So we don't need to save that. We've got our data good to go. So now we've got some extras here. So we're only going to need 25. But let's get started. So we'll go with Tracy Chapman. Yeah, we'll go with this photo. This is kind of a good. I mean, I don't necessarily agree with all of these assessments as to whether who is ugly and who is not, but okay. Alright, so Joan Rivers is going to be next. Which I don't know if that's ethical, because she, well, first of all, when she was younger, I mean, I don't think she's unattractive in her younger photos. So let's get rid of Joan Rivers. We've got plenty of people we can get rid of. Okay, and let's move on to Yoko Ono. Yoko Ono might be another one. It might be unethical to use because she's not like an actor who plays unattractive roles. Tracy Chapman likewise. And you know what? I've got a lot of extra people to get rid of, so I think I'm going to get rid of Yoko Ono. Okay, but we are going to use Rosie O'Donnell. Okay, so then we'll go with Sarah Bernhard. Okay, number 4. Yeah, this is another one I don't know if I necessarily agree with. Okay, we'll go with this for Bette Midler. That's the other thing I don't have is an age of ranges. Yeah, I don't know if this is gonna work or if it's gonna be interesting, and it was a lot of work, so I kind of don't know what I'm doing right now and why I'm doing it. It seems like there's a lot of like lesbian women on the ugly list. And just to be clear, I did not make the ugly list. I came from somebody else. I'm just using the data. Like, I did not personally determine whether Bette Midler appears on the ugly or attractive list. Yeah, it looks like it mostly just, like, it's gonna really depend a lot on your age, on that sort of thing. Okay, let's get a good Janet Reno photo. I guess this is a good one. Oh man, so much more innocent times. I wish we could just have this sort of thing happen again. Okay, I don't know how she made it onto the ugly list. Yeah, I don't even know if I can include her, but let's do it. I mean, it's not my assessment. Just because I don't think... Okay. Chelsea Clinton's gonna be a good one. But again, you know, is it ethical to have somebody who might not necessarily appreciate being on a ugly list on there? Because there are people who would, people who make their living being ugly. Okay, I don't know who Melissa Clark is. It looks like she's had dramatically different hair at points of her life. Let's go with this one. I think this is the celebrity Melissa Clark here. I'm just kind of worried about getting a photo of a random person named Melissa Clark that wasn't on the ugly list, and just making a personal assessment as to whether accidentally doing that. Because I only want people in the data set who are actually on an official ugly list, written by a human who does that sort of thing. I personally do not create ugly lists or hot lists. I do network engineering stuff, and I juggle a lot. Although I didn't juggle today, I didn't juggle yesterday. This is another one I don't think I agree with at all. I'm not sure who wrote this list. Fiona Apple, that name sounds familiar. I can't put a face to the name though. Oh, and a singer. Okay, we'll go with this one. Yeah, this one I think is a good image because it's got the different color hair, like the Nicki Minaj and the other one. Oh, is this, okay, so I don't see any really good photos here, so I've got extras still, so we're gonna get rid of Amy Carter. We're gonna move on to Tanya Harding. which is another one I'm not sure I necessarily agree with. But we'll use this photo here on the left. She really, really wanted to win that thing. Okay, Barbara Streisand, we'll use her. Okay, yep, we'll use this photo. Okay, so now we've got Maggie Gyllenhaal. Okay, let's go with the first one. There we go. Yep, we'll go with that one. Oh man, I'm starting to get tired, but at the same time, I'm almost done. Tori Spelling. Oh, did I already do Tori Spelling? I did, okay, yeah, so we're gonna skip that one, that's a duplicate. We're gonna move on to Versace. Okay, this looks like a pretty good one to use. I'm guessing she has really nice accessories. Oh, I remember this person, the Catwoman. Let's get rid of this because I mean, I guess this one would be good. Yeah, let's go with that. Especially, it looks like Joan Rivers is a duplicate, so we're kind of running out of photos to use. Okay, so now we've got a number of ones to choose from, but let's go with Tilda, and if that one's good, we'll use that one. Yeah, so this should be good. Yeah. Okay, so I think we're good to go. We've got 25 female celebrities that made it onto the ugliest celebrities list. So we'll delete those extra. Okay, and then we've got some extra men as well. We'll need to get down, we'll need to get rid of 15, but let's see if I can get through this. Hopefully, it looks like it's already 10 o'clock, which is later than I would have wanted. But
Yeah, and then if I see any hats, I'll just immediately get rid of those because yeah. Okay, so these look like they're all black and white photos. I guess I could use this photo. Yeah, let's use this one. Well, even that one's kind of hard. So let's get rid of this one. We've got plenty to get rid of because I just don't see a great photo. Okay, so we'll go with Kelsey Grammer instead. Yeah, and Kramer from Seinfeld. Danny DeVito, let's see, he's a good one. Yeah, we'll go with this. Trash man. Boy, that would suck to do this whole thing and then just at the end realize that it tells me that I'm ugly. That would be like the absolute worst, like the cherry on top of like the worst possible outcome. Okay, let's go with this photo. Okay, this looks like a good photo. I think it's ethical to use Mike Tyson or any boxer to like somebody's job it is to get punched in the face. Probably can't complain too much if somebody calls them ugly. Yeah, let's use Woody Allen too. I mean, he's kind of a controversial figure for some of the trouble he's been in, but we'll use him. All right, Rodney Dangerfield. He's going to be a good one. He kind of made a career of himself for looking ugly. A lot of comedians kind of use their ugliness. Alright, Dennis Rodman, we might, oh, yeah, we might not get a good photo for Dennis Rodman. Let's move on from Dennis Rodman. We've got to drop a bunch, and it looks like a lot of these are not going to be great photos. Ah, here we go. Yeah, this is a much better photo to use, I think. Okay, James Carville is going to be next. Alright. You should have Mitch McConnell on here. He's one of the ugliest people around. But I think these are ugly celebrities. Okay, Scottie Pippen we might want to drop as well. There's going to be a lot of kind of sports photos. Yeah, these aren't the best photos. So let's drop Scottie Pippen. We might also want to drop Marilyn Manson because he's got a makeup on. Yeah, he just looks too unusual. So I guess we can drop him. Well, I mean, it might be interesting. I mean, he might get dropped anyway because the data won't recognize him. But we could use a photo like this maybe. I think I'm just gonna drop him. We got a lot of people we're gonna need to drop. So we'll go with Tom Petty next. So this is another person who. Oh no, here's a decent photo. It's in black and white though. I guess this one I'd rather use. Either of these would be fine. Let's go with this one. Okay, Michael Jackson we might want to drop as well because he's going to look a little bit too different from every other photo. And then I don't think they're meaning, yeah, I think this is what they're talking about when they say ugly celebrity. Well, yeah, you know what, let's just use it. Okay, this is going to be number 38. Okay, we're going to use Michael Jackson. I thought Kai Schultz was on the attractive list as well. Oh, I see. This is the guy from NYPD Blue, so he's kind of known for playing an ugly role. Okay, so 39. We're getting there. Kai Schultz, I'm not sure who that is. I definitely want Steve Buscemi in there.
You know what? We can drop. Let's not drop this photo. Let's use this one. Yeah, this will be good. Okay, so he's number 40. Perfect. Okay, and then we want Steve Buscemi. It looks like Marilyn Manson is in there twice. Yeah, so this looks like a good one for Steve Buscemi. Or maybe this one. Let's go with this one. It doesn't matter. Marilyn Manson, we're going to get rid of. John C. Reilly is going to be perfect, exactly who I want for this. Yeah. Okay, and I'm getting pretty tired right now. I do sometimes wear special glasses that kind of adjust my eyes to allow me to sleep faster once I decide to go to sleep. So I might wear those glasses right now. They're going to make me look really weird, so I apologize for that. But I do need to take care of my needs more importantly than a lot of other things. Okay, so Steven Tyler's going on here. There we go. Okay, so that's but I'm very close to done. So then Clint Howard. There we go. Yeah, this is a good one. Okay, Forrest Whitaker. I kind of want to skip him. No, let's use this photo. Although I've got a lot of, I think I had a lot of bold people, and I've got 10 extra people, so yeah, let's skip him. We're gonna skip this one as well. Okay, let's go for Ron Perlman. Okay, we'll use this photo. Okay. William Dafoe is good. We might take Iggy Pop out. Yeah, let's take Iggy Pop out. Just because there aren't. Usually musicians don't have the best photos because they've got a microphone or something like that. But William Dafoe, I think, is going to be perfect. I think Danny Trejo would be decent as well.
Yeah, let's go with this photo. Well, let's go with this one here. Okay, we've just got 2 more left, so we're really close to finishing, which I'm very excited about. I'm kind of surprised he made it on the ugly list, but that's okay, we'll include him anyway. I think the algorithm might get confused that he's on there. Okay, so this guy I think I already had on there. Oops. Sometimes it doesn't copy and paste correctly. Ah, here we go. Perfect. This guy plays mobsters and villains. Really good, ethical person to have on a ugly list. Being ugly is kind of like an asset to this person because he can get film roles and stuff. Okay, so that's it. He's number 50. Yeah, let's upload this data and see if we can get it to work. So let's go on Paperspace. Okay, and we're going to need to upload it to Paperspace because we've got to train the model. So log in with my account that I've been using. I am tired. I'm no longer as hot as I was, but that's because my air conditioner kicked in. Oh, okay, that feels good. So, yep, well, we've got a notebook, so let's open the notebook. Perfect, so let's go to NBS. We're going to go to My Projects, and then we're going to create a new project. Oops, so I accidentally created a notebook. I want to create a folder. So we can delete the notebook. Okay, so now we're going to create a new folder, and the folder is going to be named Celebrity AI Identifier, or Celebrity what we'll say, what kind of celebrity are you? Upload. Okay, so now let's do upload. We're gonna put our data in there. So on the desktop, okay. Fast AI course, and then it's gonna be My Celebrity AI. So we're gonna upload these 2 folders. Oops, so
Can we upload a folder? It looks like we can only upload files, but we can upload multiple files. So let's upload all the 50 files. Oops, so I kind of made a mistake here. Instead of uploading all 50 files, I should have, yeah, so let's click cancel on all of these. So we're gonna click 50 times. There we go. So now we got one that, okay, so now we can create 2 folders. We're gonna have the first one say attractive and the next one say ugly. Okay, now we need one more folder. Ugly. Okay, so let's get all our attractive celebrities in here. So, yep, this is the attractive. Okay, so now we can click upload on all of these. We'll need to wait for it to finish before we can click the next one. So this is going to take a fair amount of time, not too much. And hopefully we'll have 50 photos in here when it's done.